Hello, can people hear me? Hi everyone, it's now 1 p.m. EST and we are on air, as there should be a little flashing red on air on your screen. And so I'm gonna kick us off and get started. My name is Neil. I am a postdoc at MIT, working with Professor Alberto Rodriguez, and I'm one of the organizers of this workshop. And this workshop is called Advancing Artificial Intelligence and Manipulation for Robotics, Understanding Gaps, Industry and Academics Perspectives, and Community Building. The title is a mouthful because this is actually an amalgamation of 3 RSS workshops that were smushed together into one. And so we have a pretty exciting agenda today. So before we get started, I just want to quickly interface all of you that are here with, get all of you oriented with the OEA interface. So you should see my screen in the middle, and then I should be on the left. On the bottom, there is a chat where you can type and the messages will be permanent. And below that, there's also something where you can send a quick reaction, like this thumbs up that I'm sending that'll just kind of just float up, hang out for a second, and then disappear. There's a green bar or panel. That's where all of you are now. If you want to ask a question, you just click where it says click to appear and ask a question, and then you will be able to speak and I will be able to hear you. And then once you're done, just please put yourself back in the green bar. And that should be it. And that's pretty straightforward. There's also a room on the side for the posters where we'll help you out when the poster session starts. So now that that's out of the way, we can get started by talking about the aims of the workshop. And this workshop has 4 aims. The first is determine important criteria for industrial adoption and the gap between these criteria and the current approaches to manipulation in academia. And the rest of these aims sort of follow from that. The next one is raise awareness for the need of machine learning metrics, evaluations, and benchmarks for manufacturing relevant parts, operations, and environments requiring robots. The third is to define a common language for discussing ML performance. This is across both industry and academia, characteristics and applicability, and/or measurements. Common language for discussing ML performance, characteristics, applicability, and/or tools and measurements science necessary to advance the state of ML in manufacturing robotics. And the last one is form an ongoing community to develop, review, test, and contribute to concepts and tools that can help foster the adoption and implementation of ML-based manufacturing robotics capabilities. In order to address these 4 aims, our workshop will consist of 4 sessions. Right after this will be speaker session 1, where we'll hear from 2 speakers. And immediately following that will be speaker session 2, where we'll hear from 3 speakers. There'll be a short 30-minute break, followed by an hour-long poster session, where we have 7 posters, followed by speaker session 3, and then an hour-long panel discussion. There will also be discussions at the end of each of the speaker sessions. So at the end of 1, 2, and 3, and those will be about 30 minutes, and they will just be limited to the presenters in that particular session. We're going to hear from 8 awesome speakers today from both academia and industry. Actually, I think we have kind of an even split if you don't count people that have 1 foot in academia and 1 foot in industry as well. These are Jeanette Bogue, Matej Carli, Danica Kragic, Arnold Kravitz, Juan Aparicio Oea, Parag Patre, Al Rizzi, and Russ Tedrick. And last but not least, I want to thank the organizers. As I mentioned, this was a sort of a beast of a task because it was 3 workshops combined into one. And as you can see, that's been a collaboration across several institutes and organizations, as well as with many people. So thank you all for your hard work. And this is basically the intro. I'm going to turn it over to Megan now, who will moderate speaker session 1. Megan, sorry, I don't think we can hear you. Maybe you're muted? Yes, you're muted. Yep, now we can hear you.
Okay, cool. So hi, everybody. I'm Megan Zimmerman. I'm a computer scientist at NIST. I work on AI for manufacturing robotics. Our first session is going to be on AI for manufacturing robotics. The whole workshop is on both AI for manufacturing robotics and manipulation, and hopefully we'll be able to tie everything into each other. The first session we have is on manufacturing. Neil, could I get you to stop sharing your screen for a second? Great, thank you. So for everybody, there is a Slack workspace that we are promoting for the community of people who work on AI for manufacturing robotics. And we're also going to be holding any conversation that can't be held within this workshop on that Slack workspace. And additionally, we're trying to get a community together to work on a resource, which is this website for people who work on AI for manufacturing robotics. Both of those links can be found right there at the top of the screen. Hopefully they're not too long to type out. But please join us in the Slack workspace if you want to discuss anything regarding AI for manufacturing robotics. And if you just want to talk more about anything that happens during this workshop and you just don't have time to ask a question, there is the place to do it. So without further ado, I'm going to go ahead and introduce the first speaker, who is unfortunately not able to make it here live, but he graciously recorded his presentation right before this. So our first presenter is Arnie Kravitz. He is the CTO of the Advanced Robotics for Manufacturing Institute, or ARM. In this role, Arnie gives ARM's technical vision. Arnie drives ARM's technical vision to help the organization fulfill its mission of increasing U.S. global competitiveness by accelerating innovative technologies that make robots more accessible to U.S. manufacturers. He achieves this goal in part by convening experts and stakeholders from among ARM's industrial, academic, nonprofit, and government partners. He has been in the field for over 37 years and is going to talk today a little bit about ARM's participation and how you can get involved and what they're doing as far as AI in robotics for manufacturing.
Good afternoon, everyone. It's a real honor to be presenting here, and I'm really looking forward to the presentation. I've been asked to talk about what we're doing at the ARM Institute, which is Advanced Robotics for Manufacturing Institute, in the areas of how we've been using artificial intelligence to enhance the performance, the proficiency, and the efficiency of robots that are used in manufacturing. And I'm Arnie Kravitz. I'm the Chief Technical Officer of the ARM Institute. So just to talk to you all about the ARM Institute first, I know not everyone is familiar with us. We are one of the DoD institutes. We are actually majority funded by the DoD's Office of Secretary of Defense. We're also funded by the R.K. Mellon Foundation and a lot of other foundations out there. We're about 310 strong consortium of the leading robotics, original equipment manufacturers, integrators, and tier 1 research universities, as well as innovators, and various government departments, including NIST, Department of Commerce, and the Department of DoD. As you can look through this very crowded array of pictures, and it's purposely crowded to tell you what a crowd we are, you can see the just who this makeup is, from 3Ms on the material side of things, to Yaskawa as a robot OEM, to IAM Robotics in the area of autonomous mobile robots, to GE, to Raytheon, to Waypoint Robotics, to Fanuc, to UR, to Texas A&M University, Carnegie Mellon University, RPI, my alma mater, and many others. It's a really great consortium. And what we really do bring to bear is the consortium of our members. The membership is our strength. And what we're really trying to do is maintain United States access to the latest robotic manufacturing and to encourage, enrich an ecosystem and a supply chain. So just to give you some of the wheeze about us to really get us, we accelerate the development and adoption of innovative robotic technologies. We make robots, autonomy, and AI more accessible to U.S. manufacturers. We like to say we're democratizing the technology. We nurture an ecosystem. The ecosystem is probably the most important thing we do. We introduce to the DoD OEMs, to new suppliers. We create relationships by forming teams to work on our projects. Small companies and startup companies that join the Institute, we will help them get their relationship with a J&J or a Raytheon through working on one of our projects together. We convene workshops and technical interchange meetings to identify, understand, and prioritize the technology gaps. And I'm going to go into that because we're developing new capabilities, but what prevents capabilities from emerging is a technology gap. And we try to solve that technology gap through investment in technology. And we develop technology to improve, as I said in the very opening, the performance of the robots, so the robots perform better, the efficiency of the manufacturing line, so the line actually is more efficient in how it works, and the proficiency of that line or those robots that are used in manufacturing. And proficiency is the ability and the accuracy of how well they manufacture. It's the skill of manufacturing. From an AI perspective, which we're talking about today, we really view AI in a very narrow perspective. We are really interested in artificial intelligence that enhances the performance, efficiency, and proficiency of robots that are used to perform manufacturing processes. And that includes logistics tasks. Because, for those of us who work in factories, we get the autonomous mobile robots, which are doing logistics tasks, are part of the manufacturing floor. But some people who don't work in it may not realize that. But we are everything from fabricating, finishing, assembly, and inspection processes to autonomous mobile robots that scan, map, model an environment, to robots that do repair and maintenance. Because when you manufacture things, you make mistakes, and sometimes it has to go through rework and repair. So the sustainment and maintenance community really falls underneath us because of the overlap of technologies. We're very interested in robots that handle material, 10 machines. Fetch. Kit is when you put disparate parts together into a little bag, deliver them to a workstation so that the worker can assemble them. Store, pack, unpack, load, and unload. We also have a very large EWD organization. When I say large, I mean in accomplishments. We work with our Educational Workforce Development Organization. We've been developing a framework to help define what is the educational needs of a future worker in robotics. Because it's really, in our view, it's fairly pointless to develop advanced robotics manufacturing or advanced robotic technology for manufacturing if you can't skill a workforce to use the robot as a tool. And we see robots as tools for workers to use. So our mission really is what drives everything we do. And our mission is really simple. It's to enable the U.S. defense and commercial industrial bases to become the envy of the world by developing both advanced robotics technologies and, most importantly, a U.S. ecosystem that can further develop this technology and use it for manufacturing to great advantage. We really have 5 principles in here. One of them is really just to use our facilities, but our key strategies are to guide our investments. And we guide our investments through a strategy, through a roadmap, and member and partner recommendations of which should be in our calls for proposals. One of the most powerful things we can do is to convene the consortium into workshops and technical interchange meetings to give a fresh perspective that's highly educated, people with boots on the grounds who actually use robots to manufacture, who use AI to enhance the performance of those robots, to develop roadmaps or to solve other problems for the consortium, for its members and its partners. And the partners are the U.S. government, the DoD, and other organizations. And to develop a technology and business ecosystem, again, to support this robotic manufacturing adopters. It's very important that the industry knows each other, is able to form teams quickly to solve problems, and can work together. And again, as I said earlier, we introduced the DoD to an expanding supply chain to non-traditional suppliers. So for like to, joining an institute is a great way efforts so that the educational workforce development tools and frameworks that are being developed will meet the needs of the technology that's being developed so that they stay in sync. We look at multiple domains and applications that are driving the future. So we kind of look at this as the big funnel, or some people call this the cake. At the top level is the domains, which is, the DoD and the commercial manufacturing environments. And at the applications layers, it's aerospace, maritime space, autonomy, artificial intelligence, automotives, textiles, energy. And at the capabilities levels, it's fabrication, finishing processes, assembly processes, inspection processes, and material handling processes. So it's all those logistics areas, as well as all the traditional manufacturing processes. And the technologies that we're interested in, we look at the intersection of capabilities and technologies is we're very, very interested in the human-robot interaction and the robot-to-robot interaction. I used to keep them separate, but I've combined them because in many regards, they're very similar. A robot doesn't care whether it's dealing with another robot or another person. We want to make sure that those interactions are safe and efficient. In terms of intelligent robotic systems, it's making them smarter in all levels. And I'll go into where we've worked in this. And in terms of dexterity, having manipulators being able to have the capabilities of the human hand when necessary. It may not need that, but if it does, we'd like to improve the dexterity and mobility of the robots. And then reconfigurable robotic designs, to design robots so they can be easily reconfigured for other applications and other uses beyond just automated tool users, and using the artificial intelligence to decide which tool to pick. And then modeling, test, and AI data. The democratization of databases is very important to encourage the industry to move forward and grow. How do you test these AI databases? And using models to do verification and validation or pre-commissioning analysis so that when we get to commissioning, we're very confident we'll actually pass it. So what we found really interesting is we've done about 60 technical projects to date. And 30 of those projects chose to use artificial intelligence in their solution. We do not require any project to use artificial intelligence. And that was kind of profound because it gave us this very large database because we collect metrics. So we have this very large database of metrics for artificial intelligence, and our metrics working group is working on that now to say, what are the relevant metrics for assessing performance, efficiency, proficiency, and many other areas with regards to artificial intelligence when you're using it for robotics and manufacturing. Where we found the artificial intelligence was most prevalent on our projects was, and I don't think this will be a surprise to most of the people in the audience, but in terms of path planning, determining the optimal path or the best path for the arm and the end of arm tooling as it will progress across the surface to do whatever manufacturing process it is, whether it's sanding, polishing, grinding, or cutting, or welding. And the other one was path planning for autonomous mobile robots, which most people are most familiar with. How do I navigate a autonomous mobile robot through the choreographed chaos of a factory while I'm sometimes connected to the cloud, but I'm often dropping my connection to the cloud because people are walking around, and let's face it, it's a factory, so I'm going to go through dead zones. How do I use AI to most efficiently plan the path of my autonomous mobile robot so it can quickly get from point A to point B without causing a safety issue for any person working in it? And again, a lot of times we use we call the lawnmower motion, but how do I path plan across a surface that's curved or curvilinear, so that we call it the lawnmower path planning doesn't quite work. So again, we use artificial intelligence in those areas and to learn how to do it better. The other area is inspection. Artificial intelligence is very good at spotting a defect in a object under manufacture, either by spotting wiring that's incorrect, or subtle things such as a crack or a pattern that's subtly wrong. And how do we teach a robot to know the difference between an acceptable, I'll call it blemish, which is not a defect, and a blemish that's a crack and is a defect? So, again, when is a polish a perfect polish, and when is a polish imperfect? They're very difficult things, and it's a great area for machine learning and artificial intelligence in particular, as well as also in the deep learning as to when is a crack a defect versus when is a crack. It's just a slight crack that's imperceptible. In terms of mobility, again, that was another area where a lot of artificial intelligence was chosen to be used in control algorithms when the states are not as predictable, or the environment is in flux and not completely predictable, more of a stochastic environment. And then in the human-robot interaction for safety, and in human-robot interaction for predicting how the human might behave in a certain area. Those are the areas where we're seeing it show up in our calls. And it's not because we're saying you shall use artificial intelligence. It is because people chose. Now, I would point out in our current call on the street, for those of you familiar with us, we actually do have a call on the street for artificial intelligence. So again, we went back and we talked with folks as to why they use the artificial intelligence. So I just described where they use it. This was why they use it when we interviewed, again, it's 300 plus people, but there was about 50 organizations in the 30 projects that were using it. Some use it heavily. And the reason that they chose artificial intelligence was conventional methods that were performed by using conventional methods performed by humans were found to be too slow and error prone. And the artificial intelligence enhancements made those robots work more quickly, so it made sense. Okay, so good. The next one was the new development. If you go look at the tools that are available when you buy soft cores or when you buy chipsets, the new development tools that are out there, those software developers' toolkits are greatly reducing the programming effort, and it brought in modularity and flexibility. So again, it's really the way the industry is doing design. It became easier to use these AIs because they're pull downs or they're drop downs. And AI was capable of handling tasks with a variety of conditions I spoke to earlier in the last slide. Whenever you have a stochastic process or a stochastic condition where you're not quite sure how it's going to come out, but you have a pretty good idea, artificial intelligence is a great way for handling those tasks. And the ability to be trained, to learn, to anticipate actions, and to continuously improve its performance over time through machine learning or through deep learning or through shared learning. And AI solutions can distinguish coherent and subtle differences between conforming and not conforming surfaces. So a couple of the projects we funded was using scanners to conform products to their drawings, or to take a product that doesn't have a drawing and recreate the drawing based on looking at multiple products to get what was the drawing that these samples were built to. So just to give you some examples of projects that utilized artificial intelligence to enhance robotic manufacturing, to enhance the performance of those robots. to enhance the efficiency that it provides to that assembly line using the robots, or to improve the proficiency of the robot when it's manufacturing or shape forming or shape finishing, as well as workplace safety. So the key technologies that we look at, and you'll see this as my slides go further down, is we have a technology taxonomy, and I'll go down to in more detail in the next slides. But the main categories of our taxonomy are human robot and robot interaction, intelligent robotic systems, dexterous maneuver and manipulation, reconfigurable robotic design, and then models, data, test, and evaluation tools. And if you look where we've done projects, these are just some examples. We've had dual cobotic work cells where multiple arms assemble and inspect trays and then pass these trays to the coworker, and the coworker then pulls things out of the trays to prepare them for integration. So it's a very complex thing. So not only is the robot doing pick, place, kitting, and assembly of trays, it's working right next to a human coworker and then passes them the tray when it's put together for the human to do a function on it. We have developed an OEM agnostic teach pendant for new or obsolete robots, which if you have a bunch of old robots that you can't get parts for, is kind of a godsend. And this was developed up in upstate New York with a bunch of folk up at RPI. And it was originally developed to run on like a Raspberry Pi or a small single board computer, but we've actually developed it now to where it runs on a laptop, on a tablet. And AIMR, autonomous mobile robots that use what's called safe technology to, again, meander across a factory or around a factory through people picking up scrap and then bringing it to an area. Very difficult problem to solve, multiple types of sensors to use. And those were all in the human robot and robot-to-robot interaction. And the intelligent robotic systems was a robot that could look at an object in a factory and fingerprint it by looking at it, by looking at the detail, the attributes of an image, fingerprint an object, and then if the object gets lost, be able to search the factory to go find the object by making we'll call it a fingerprint of the object. Things for testing where they evaluate, liquids that were splattered, and this was one we did for COVID, was a blood splatter test, where we used AI to, again, look at does this pass or not pass a specific test. And visual quality assurance. Again, I talked about this earlier, detecting micro defects on shiny parts. Very, very difficult to do by a human, incredibly difficult to do with machine vision. But we worked very hard on this one and was developing artificial intelligence for excuse me, how do I spot a micro defect in a part? Those again were machine learning and deep learning. In terms of dexterous maneuver and manipulation, one of my favorites is snake robots that can swim through flooded areas and swim through pipes. Another is a 3 cobot arm that can lay up composites to make very complex composite shapes. And another one is lights out manufacturing or near lights out manufacturing, where the whole line is a mix of automation and robotics. In this case, we did one with composites, where we did the full composite process, including bagging and debulking. And in the area of reconfigurable robot design, we haven't done as much there. But again, on the AI here, it was reconfigurable pick and place robot. This is a fellows program we're funding in Pittsburgh. And this project was done by Capson Robotics, was to develop a robot that does pick and place and assembles kits. And then you can move to another work cell. It'll look at its work cell, survey itself in, identify the parts, take its new program, and it's already self-calibrated in. So it's using its onboard sensors to set itself up in the new work cell, which saves an awful lot of time. And lastly is model, data test, and evaluation tools to benefit. These are tools that help you decide whether or not to purchase and use robotics in your factory. These are the tools that can do the pre-commissioning analysis to say, yeah, there's low risk to commission. These are things that will help you figure out how to lay out. What's the best layout for your factory? So a lot of tools, and this is in the area of data where it's a very interesting area. And again, these are just some examples of the types of projects that we funded. So we develop CDIP. We have a really unique way to handle IP at the ARM Institute. Whatever IP you bring into the Institute is yours to keep. We don't own it. Why would we? Any IP you develop, and I mean intellectual property that you develop while working on a project at the ARM Institute, is owned by the prime and the team that developed it. And any intellectual property you develop after the ARM is funding is yours to keep. We ask for really about three things. One is because the DoD funds us on the intellectual property you develop with ARM funds, we ask for government purpose rights. For the IP that we develop with ARM funds, we ask that you share it across the membership for research purposes only. And we ask that you license it to each other, but we don't get involved in the licensing. So if you really don't want to license it to someone, you would negotiate very hard on what would be the license you would accept. And in that case, your arch competitor has become your partner because they've agreed to the terms that you thought you would accept. So if you really look at how we break it up from a taxonomy perspective, it's software modules, it's software programs, it's AI databases, it's evaluation of tools and sensors, it's technical design packages, it's IP protection instruments, and then we have market surveys, photos, and videos. This is all available to everyone in the membership online that has access to it. So for software modules, we're big advocates of ROS, Robot Operating System, ROS Industrial. And so we have a lot of ROS modules that we've used in our things, and we've actually improved some ROS modules in their repository. We've also got in there several significant custom software modules and open source software modules. And these are things like, just to give you an example, some of the more popular ones are a fleet manager, a software module that manages fleets of robots. We're working on one that'll be in there that will be OEM agnostic. It's mapping modules. It's control modules. It's path planning modules, simple to more complex. It's machine visioning modules to help you identify things. Those are the things that you'll find in there, and I've got them laid out. In terms of the ROS, you can see there's a significant number of ROS ones. Those are in the middle there. In the software, it's the runtime software for a specific capability. It's the application programmer interface and the software developers toolkit. There's third-party software licenses, and there's virtual test environments. And the AI databases, we're trying to get to trained AI databases. Again, we're looking at this democratization of artificial intelligence, and we're trying to get to some neural networks. These are the types of things we would like to see in our CDIP, and some of these things are already there. And the evaluation of tools and sensors. On the technical design packages, again, we want, for the projects we funded, system specifications, CAD designs, and reference data sheets. If there is IP protection, there's the patents and the copyrights, so you'll know what they are. And again, market surveys, photos, and videos. There's a really wealth of information in that data repository. You need to be a member to access it, and you need to follow the rules, but it is available for folk to use on for research. And I think that what I don't have on here, but wish I did, the most important information we have in here is the company and the researchers that did the work. So if you want to use any of this, obviously the best way to do it is call the person that developed it and get them on board your team. So we use these things called discovery workshops to help define things. And it's one of the things that we're doing a lot. With 310 members that really are some of the who's whom in industrial robotics, it gives us the ability to provide a very nice service to the ecosystem. So discovery workshops, you'll hear me use this term a lot. It's an approach for leveraging the membership and partners to create roadmaps for a topic. And that's what really comes out of these is taxonomies, roadmaps, and program plans. So if you really just look at the way we do a discovery workshop, and I drew a little picture here at the top, it's AI and robotics, because that's what we're talking about today. It could be space, it could be something else. And then we have the U.S. industrial base and the modernization priorities, which is what we get from the scope of experts in the topic area. And then we look at robotics, and then we look at all elements of manufacturing. So if you go from the bottom up, we're focused on manufacturing using robots for the U.S. industrial base in the area of topic, which is the top of the pyramid. So discovery workshops, we convene a gathering, and I really have to say esteemed practitioners and experts who are members of the consortium or partners. And partners are everybody in the DoD or in the U.S. government is a partner, to discover key elements for some sort of an ARM technical strategy. We just finished up the AI one. My goal at today's briefing was actually to be out briefing that, but we're not done and it's not ready to be released yet. So the goals are to support the development of technology roadmap for advanced robotic manufacturing, as I just said. But it's also to forge the strategic alignment between the partners and the consortium. Because I like to say is we make consensus decisions. Our roadmaps are consensus roadmaps of the partners and of the consortium. They're not roadmaps of the staff or myself or other opinionated people that work for the ARM Institute. They really represent the consensus view of the consortium. And they always are with respect to robotic manufacturing to address the modernization needs of the U.S. industrial base. So our method really was simple, but I think different. I've been to a bunch of road mapping and workshops recently that focus mostly on only the technology. We focus on the intersection of what I like to call capability and technology. And the intersection is based on a simple premise. I like to work backwards. I like to ask the simple question. If only you had this capability, fill in the blank, what would that capability be that gives you some sort of a disruptive advantage in the marketplace? What's that key killer capability that will bring your company to the next level? Mind you, framed it as robotics for manufacturing. And can that capability be instantiated using robots? And if so, why can't you build it? What's preventing you from making it? And then often the answer will be a key technology. Excuse me 1 second. Captain, stop that. Get over here. Oh, sorry about that. I have dogs in the, yeah, let me grab them. Okay, and I'll wait 2 seconds and then go. Okay, good. Megan, am I good to go? Okay. So again, we focus on the intersection of technology and capabilities. And the reason we focus there is technologies are what enable capability. So if you ask yourself the simple question, can you imagine a capability that would give your factory, if you had a robotic factory, can you imagine a robotic capability that would give your factory a breakthrough advantage that would be disruptive in nature and bring your company to the next level? And if you can imagine that, why don't you build it? And usually the answer is a particular technology doesn't exist. Those are the technology gaps that we're interested in, and that's where we focus. We don't just focus on technologies, we focus on technologies that solve major capability needs. And that's what we do at the workshops. The workshops review, consolidate, and prioritize the responses along technologies, and the teams build plans to develop these AI technologies to construct the roadmaps. And that way, the team owns the roadmaps. It's not an ARM roadmap. It's a consortium roadmap. It's that consensus roadmap. And then, of course, the teams brief it out, and then we work on it together, and we're done. So I talked a little bit about this. Is a kind of a complex chart. I'm really trying to get that message across that capability needs at TRL level 7 are fulfilled by developing and maturing technologies from tier level 4. So we look at and ask the simple question, if only I had this capability that would give me that disruptive advantage, why can't I bring it to reality? And the answer is the technology doesn't exist. And we look back to say, well, what are those technologies? And then we group those technologies and we focus on investing in those technologies that give us the highest payoff or payoff to the highest number of relevant capabilities. And just to give you an example, So we've come up with this concept of a creative matrix, and this is one for artificial intelligence. So again, what are the manufacturing capabilities? Well, they're always going to be the same. If you manufacture, you fabricate things, which is shape forming. You finish things, which is shape finishing. You assemble things, which is like bolting things together, welding, sewing, gluing. You inspect at every step of the process, from you inspect while you're fabricating, while you're finishing, and while you're assembling, to inspect finished goods to make sure they match the drawings. You have material handling robots that kit things out and bring things all around the factory to the work cells, as well as tend to the machines that are manufacturing. And we have this area we call infrastructure. And infrastructure is metadata. It's middleware. It is software that allows multiple robots to work together, but it fits all of the other capabilities. And we call those infrastructures. And on the technology side, these are human-robot interaction and robot-robot interactions. We break those up into that taxonomy. Intelligent robotic systems, dexterous maneuver and manipulation, reconfigurable robotic design, and model data and test and evaluation tools. And we break those down further. I won't go through all these, but all the ones that are colored in yellow are relevant to artificial intelligence. The ones that are in black are not. And that's because the bottom one is a standard. It's another thing. But for wherever you have hardware and software and data is always applicable or can be improved or enhanced through the artificial intelligence. So the HRI, RRI, or the human-robot interactions, those are things like intuitive interfaces to help you human-robot trust and safety, many things in that area. The intelligent robotics intelligence is distributed edge and cloud computing. And then one of the areas that's very popular is this advisor robot, which observes, identifies, fault detections, and training. In dexterous manipulation, it's really that path planning of the arm or the end of arm tooling. And in the reconfigurable robotic design, it's libraries, data libraries. It could be a trained AI databases. And methods, data, and test and evaluations. It's intelligent tools that help you make decisions to use robots. And then I'm going to skip this slide because I actually just briefed you through it on the last slide there. And the taxonomy of robot manufacturing, I really didn't get into this, but what is fabrication? What is finishing? What is assembling? What is inspection? What is material handling and fetch? So fabrications is molding and castings. It's additive manufacturing is fabrications. It's stamping things. It's composite layups, both wet and pre-preg. It's forging and folding and bending and tinkering, which is metamorphic manufacturing. It's cold working and spinning, turning, etc. Finishing is really, after I've formed a shape, finishing is literally what it sounds like. It's I take it out of the mold, I deburr it, I camphor the edges, I sand it, I grind it, I polish it, I clean it. And then there's surface finishes, which are like painting and coating, de-dusting. I take it out of the additive printer and has to be de-dusted. Cold spray and masking so that I only finish the areas I want to finish. In assembly, it's aligning, welding, thermoplastic welding, brazing, soldering, bonding, sewing and stitching, pinning, etc. In inspection, it's visual. It's all of the senses of inspection, from visual to acoustic to touch to a comparative inspection. For confirmation, I inspect it and I compare it to a drawing, or I inspect numerous copies and create a drawing, and then I inspect stuff back to that. For obsolete parts. And then material handling and fetch is all the pick, place, load, unload, stack and unstack, which is pack and unpack and palletize, as well as transport and balance. So we have been working this now for a while. We're about to come out with our largest roadmap. Our current roadmap came out in around late 2017, early 2018. We're about to replace it. They'll be organized by fabricate, finish, assemble, inspect, infrastructure support. They'll also be augmented with artificial intelligence, autonomy, and space, which are future roadmaps that we're in the process of making now. And I'm not going to walk through this part here. These are the key technologies I just talked about. So everything we look at is that intersection of capabilities and technologies. In order to get a particular capability, what technology do we need to develop? So the discovery workshops, what I really wish I was able to brief out to everyone today, we've just finished it up. It was a multi-step process based on that creative matrix. We had about 20 people that we invited through a process where we were advised by our technical advisory committee, our government partners, and the membership community to find, I'll call 20 boots on the ground people who use artificial intelligence to enhance the performance, proficiency, and efficiency of robots, to really look at what would our roadmap be? What is the taxonomy? So the first thing we did was we created the creative matrix. We pulled this wonderful team together. And by the way, there were 20 people at the table. Many of them had teams of 10 and 15 back at their sites because we did it virtually. And the first thing they did was they filled in the creative matrix to say, what are the needs that are out there? If I only had this one technical need, what would it be? And we actually got 300 of them. We then grouped those. First, we formed an advanced taxonomy. We then grouped them. We then went through the groups and we combined things that were the same, things that came up in different working groups that were the same, and we prioritized them. And the priority was based on impact if we make it versus difficulty. So there were things on there that were really, really difficult but had a ton of impact. Okay, those got funded. But there were things that were really, really difficult and had no impact. We didn't fund those. And so we ended up coming up with this area of, if it's really, really easy and has some impact, we'll fund it. Really, really easy, have a lot of impact, definitely fund that. Really, really hard, but has a lot of impact, that will get funded. And the output of those was we developed program plans to develop it, and those created roadmaps. And that's where we are right now. These roadmaps have been built. We're in the process of final review, and they will be coming out to the ARM membership probably by the fall membership meeting. So just to give you an example of what we used, it was a simpler creative matrix, HRI or RRI, sensing and perception, mobility and control. And we filled this in, which was basically said, what was the capability need, or how could we improve assembly collaboration by using human early action and detection framework? So human-robot interaction applied to assembly. What are those future capabilities that if we only had them would make a marked difference? And we filled the matrix in, and that's where we got close to 300 really high-quality returns, which we then filtered down and combined to where we ended up with prioritizing these capabilities on here, and which we then worked into the roadmaps. So just in summary, Discovery Workshops are a strategic tool of the Institute to leverage the membership to identify where to invest in technology, and specifically where we'll have the greatest impact on the U.S. industrial base. We use it to leverage our membership and our partners. Remember, it's 300 strong. And it's really some of the best in the country. We focus on the confluence of capability and technology, again, looking for those technology gaps. And where are we going in the future? Well, we're just finishing up AI. Next time I speak with you, we'll probably be talking to you about AI in space. We'll have roadmaps for those, autonomy, and others. And when we say space, we're talking about using robots to manufacture components that will go up into space. And with that, I'd like to thank you for having me brief you. I look forward to working with you all in the future. And if you have any questions, please contact us. I'm going to just read you. And if you have any questions, please contact us. My contact information is on the charts. And you can reach me at Arnie, arnie.kravitz@arminstitute.org. I look forward to hearing any questions you have. Take care now and enjoy the conference. Bye-bye.
So our next speaker, we're going to hold any questions for during the discussion session. Unfortunately, Arnie won't be able to answer questions himself, but we do have other people from ARM who can answer any ARM-related questions. Our next speaker is Juan Arpicio Ojea. Juan is the Vice President of Product at Ready Robotics, a company that develops and supplies innovative automation solutions. Juan is responsible for guiding the company's product strategy. He focuses on advancing Forge/OS into a widely adopted cross-brand robotics and automation platform that accelerates the distribution of industrial automation. Juan also managed more than 20 strategic university and startup collaborations and ran various government-funded products for ARM. He began his career at Siemens in 2010 and first worked as a software engineer and a project lead. He designed and developed tools and models used for assessing smart grid communications deployed in complex environments. So Juan, whenever you're ready.
Juan, please take the presenter spot. Just drag yourself into that upper left-hand corner. We can't hear you otherwise.
Can you hear me and see me now?
Perfect.
Awesome. Okay, let's start. I would like in these 20 minutes to take you in a road with me on a road with roadblocks, the roadblocks to deploy AI-based robotic applications in manufacturing. I will show you a bunch of videos. I hope it's a little bit also entertaining, and we can also, because I always like to see robots moving, so you will see a bunch of them for sure. And I will take any questions either online or offline. Now, just another 2 sentences about myself, apart from the great introduction. As Megan said, I am part of Ready Robotics, a company that is developing the first operating system for robotics and automation that goes across all platforms. Before that, I had the luck to work and lead a team of researchers and engineers at Siemens Technology, and you will see a lot of their work also in these slides. I'm also part of the technical advisory committee of ARM, linking to the previous presentation from Arnie, and also part of the A3 AI Tech Strategy Board. So a lot of things are also, you will see also my view on those topics. Also, I had the luck to work with some of the best professors in the world working in AI and robotics, like Ken Goldberg or Sergey Levin, Janet Bock, that you will hear later. So also some of the work that I will present is from those collaborations that really started with a question of, can deep learning revolutionize the world in robotics in manufacturing? So you will see that with some answers along the presentation. Now, to start with, in preparation for this talk, I asked a question on LinkedIn on what is stopping you to deploy ML-based robotic applications at your manufacturing facility with these 4 options. As you can see, they are pretty much the same answer, all equal. Either people think that the non-deterministic behavior is a roadblock, or there is no way to debug. It's a black box. So if something goes wrong, what do I do? There are multiple edge cases. Or, hey, the current approaches work best. So why would I need just to jump into the hype if what I have works well? So I will go one by one and try to address them. First one, current approaches work best. I will play this video in a second. You will see a robot tending a lathe at the Stanley Black & Decker facility. I will argue, guys, if you go to a factory, if you can control your the the way that you are feeding the parts, right? Inside the input to your process and the output of that. You will be much better if you don't have a camera, and obviously much better if you don't have any deep learning involved, right? Because what you care in automation at this point is precision and is speed. And these things only slow that down, right? If you had a camera process or any other intelligence in the loop, it will be naturally slower. So if what you are just doing, like in this case, you are feeding bars into a lathe, you can do it with traditional good old-fashioned controls and industrial automation. Now, let's say that you really want to use a camera because you need it in your process, either for sorting candies or pancakes or chips. In these 3 videos that I'm showing now from top robotic brands, then as you can see, you can also be very fast, right? Either there are Delta robots that work extremely fast, no AI needed, good old-fashioned kind of machine vision. You detect the geometries are easy enough to be detected. You just pick and place. And even in the example in the bottom left corner from KUKA, if you can afford fixtures, it's quite straightforward nowadays to create rules with force and torque sensors that enable you to do complex assembly like that one that you see in the video. Adding complexity, let's say, as you see in the video, all the objects are individualized, right? They are sorted out. They are not in heaps. So what happens if the objects are fed in heaps, right? All together, you still have solutions out there in the industrial automation realm that enable you to individualize components, like the videos from Flexible and Cyril here in the screen, where there are some balls, some surfaces that vibrate, like you're seeing now in the screen, and then the objects get individualized. Okay, but what if, right? You cannot individualize the objects. Either your ROI gets too expensive if you add these components, or you cannot control the way that you get the boxes of material. Still, there are current approaches, like what you see in the screen from SIG or from Kians or from Picket 3D, using CAD-based 3D shape matching that work quite well. Actually, they leverage the fact that these parts have some geometric features that are easily identifiable, and then you can still pick them from a bin. Now, what if, like, if you want to, now, let's say, pick up clothing? I mean, that must be impossible, right? That must be impossible to pick it with traditional approaches, right? And there is a lot of research on that domain, right? The first video is from Columbia University on how you unfold a piece of clothing. And the second video from Jeremy Maitin-Seffard and Peter Abil, among others in UC Berkeley, that video is from 2010. And look how amazing that was, right? You will think back then that we will have robot folding or clothes by now, but they are not doing it, right? If you go to any textile plant where you are producing t-shirts, for example, it's all manual, right? Robots are not up to the task because there is so much variability, right? It's really, really difficult to manipulate things with so many degrees of freedom. But do you need to, right? And that's where also other approaches work very well. And the videos in the bottom are from a company called Subo, a startup based in Berkeley, that has produced a method to stiffen fabric, and then with some materials, and then they dissolve in water, and voila, you have a t-shirt. And the video on the bottom right is a project funded by ARM together with Siemens. The PI was Gokul Narayanan, and also together with Subo, where that process is now industrialized at the Blue Water Defense Facility in Puerto Rico. The bottom line here is that's where the ingenuity happens, right? There are years and years of good industrial automation that, for example, that have been matured in industries like automotive. If you can leverage those, you will be much better than adding new methods that still need to be mature. So then the next question, natural one, is, and then the conclusion to that is, in manufacturing, most likely you will have CAD files, the entire modeling of your plant. So if you design for robotic automation, you will be much better using traditional approaches. But then what are we doing here? Like when to use deep learning-based methods or AI-based methods, right? There are still cases like what is now showing on the screen from 50 Siemens, where you don't have the CAD file, like intralogistics. This is not a secret, right? It's not something that is new. There are tons of startups now in this domain producing and with solutions like Vicarious or Ambi or Osaro or Covariant. I mean, I could spend 20 minutes of just naming startups in this domain because it's a very hot topic, right? Particularly driven by intralogistics, where you cannot control what is in your bin, and you still need to pick it and place it, right? But an important lesson there is, and takeaway is, the price of being wrong is not too high, right? Nobody cares about the successful picks. It's a metric that is good for a paper. Nobody cares in intralogistics. What you care is the speed of the system. If you fail 10 times, but still you are faster than a human or comparable, that's fine, right? And that's not a secret also why a lot of these companies, first of all, they try to do picking with the suction cup, right? Because it's very forgiving. In the surroundings of the optimal gripping point, you will be most likely lucky just to grasp it. So even if you miss, that should be fine. Another good example will be to pick from cells. I found a lot of videos on the internet trying to or solving the case on the picture in the back, where it's a very nice self, everything organized. But I don't know, your supermarket, mine doesn't look like this. It looks more like the picture on top with the ice creams, that everything is disorganized, and still robots are having a hard time there. Another very good example for where to apply deep learning, again, where the price of failure is almost none, is recycling. This is from Fanuc and Waste Robotics. Amazing work where, yes, you just need to identify the parts that can be recycled. If you miss one part, it's not the end of the world, because the comparison point, right, is you don't recycle at all. So you are always better. That reminds me of the same thing that iRobot did with the Roomba, right? Initially, it was targeted to a market where for people that were really love cleaning and were very intense on that. And that was not the right market. The right market they discovered was students, because the baseline was, I don't clean at all my room. So if I clean a little bit, I will always be better than the baseline. We have to also remember, when we are comparing with today's approaches, that human hands are incredibly dexterous, right? And some of you may have seen this cortical homunculus representation that represents how humans will be if our body was shaped in the same proportionate to our sensory terminations, right? So we have a lot of dexterity in our hands. That's why these hands are huge. Also in our mouth and other parts of the body. And that's because, I mean, many years developing these hands. And if you can see also the video on the bottom on a PCB manufacturing, like humans do a lot of things. They, for almost for free, would also pick up a part. They will see if it's well, if the quality is good. They will get parts from the back. They will insert it, even if it's very small, and feel the force, very small forces, as you are seeing now in the screen. There hasn't been a lot of development on the gripper side. Most of the grippers, as you see today, are still these two-finger grippers that were developed years ago. One would argue that still tactile sensing, like the research that is done by Alberto Rodriguez in MIT, is extremely impressive, and that will help to increase the dexterity of our grippers, or things like soft grippers, like the one developed by the gripper company. But I'm not so sure that's the bottleneck now of automating more tasks. As you can see now in the videos on the right, these are two examples of teleoperated robots with very clumsy grippers that they can do their work just fine, right? The key is there is a human in the back controlling things, right? There is a human in the back taking care of the autonomy. If you are from Berkeley or have been there, you may also have seen the Kiwi robots that are delivering things from one part to another, from the restaurant to wherever you want it. And those are controlled from Colombia, actually. So you remove all the autonomy part, that is the hardest part, but still you have a product. That's very ingenious, as you can see also in this robot from Japan that is really completing an order from a shelf, but is teleoperated. So that was regarding the current systems work best. Again, when we, like a takeaway, when we are introducing a new technology to the world and say, hey, this AI method will revolutionize the way that we are handling things in manufacturing, just please compare it with traditional methods and see, because they also go a long way. And we are producing thousands and millions of products today with that technology. Non-deterministic behavior. Here, the issue is in manufacturing, right? Industrial automation, you control the throughput, right? You know that you are going to get 200 cars per hour, and that's it, right? It's precise. If you don't get those, it's that you have done something wrong. But if you are using an AI-based method, you don't necessarily know. It will be a range, right? Because it depends on what is in your order, for example, to fulfill. And there's a big difference between being an observer and being an actor. When you're an observer, I mean, everybody has seen this kind of technology, I think in the last days from Brickit, I think it's a group of researchers from Russia. Super cool. You put a pile of Legos and it tells you what you can build. And it identifies what Legos are there, right? Again, the price for being wrong is not a lot, right? You don't, you maybe not get you get a part wrong, but nothing breaks, right? Same idea was a project also funded by ARM that we did. My colleagues back then at Siemens, Tao Kui and Justinian Roska were leading this project together with Itanco and Heavy Robotics, where, and I have seen this problem in all manufacturing, in all factories I have been. You receive some shipment, you open the case, you have some parts, you put it in a shelf, and then how do you trace it, right? How do you track it? So that was the problem. The solution was the team tested different neural networks and found out that the mask RCNN developed by Facebook was one of the best with accuracy of 90%. You will say, okay, is that good enough or not? Right? I'm hearing all the time that in manufacturing, I need 99.999% precision. Well, again, if the baseline is, I don't know where my parts are, and now I know with 90% of probability, is much better, right? So I can design a system. That's where the art comes instead of the science. I can design a system that still adds value to the customer with those probabilities. That's on the observer side. I'm just looking. Interacting with the physical world is another world. And you will see now in the screen a bunch of robots failing miserably in tasks that my 3-year-old can now master. But it's hard, right? Because contact dynamics are hard. They can be improved with some methods, like really, here in the videos, we were using meta-reinforcement learning or residual learning for just applying still things like model predictive control for most of the path. And then just when you are touching the part using reinforcement learning, accompany with simulations. And the same in this video, that was some work led by Gerrit Sottler, Tobias Johannik, and Eugene Solojo, where we used meta learning for doing these tasks. And still, this is the NIST benchmark. Very cool that just in 20 trials, you can master this. But that's where the gap between research and manufacturing happens. There is still a long road until this hits manufacturing, because you have to make it reliable. You have to make it precise all the time. I don't bother reading these graphs. I can tell you they are all predictions of self-driving cars. They were all wrong, right? We should have millions of self-driving cars out there by now, and as you know, we don't. And that same happens with AI in manufacturing, right? When I think as a community, we have to do a better job to set up the expectations, things take time to mature. It's very different to show a video out of 10 that it works on YouTube versus it works 24/7. That's what you need a TRL 7 to 9. Now, the last two, edge cases and black box, no way to debug. I would like to join them together. So for the first one, edge cases. And I'm taking this awesome, great tagline from +1 Robotics, robots work, but human rule. And I think that's the mistake that autonomous cars are taking sometimes, that driverless doesn't mean humanless, right? You still can have a human for edge cases. When something goes wrong, you can have a human, call a human, and it will take care of the edge cases. So you may have, instead of a robot to human, 1 human per 5 robot stations. That's fine. Or what you see also in the pictures on the that I am now pointing, there are also intuitive ways to have user interfaces that really facilitate that. So, for example, if you are doing this like cut to path from RobotMaster, very useful tool, you can have a very complex path created with an offline tool. But then if the final touch-ups, if something goes wrong, or if you need the real world is slightly different than your model, you can still enable a human to do that, right? The same thing for one of these blocks can be a very complicated AI-based speaking, but it still is embedded into a logic that the user can understand. The human can actuate and solve a problem without the need of calling the only AI expert in the entire company or your provider that may take weeks to solve a problem. And that's an important case also for the explainability part of things that people highlighted as a problem, right? We need more explainability. This is a work by Jack Huckabee when he was still at Georgia Tech. Now he's at Ready Robotics, creating a taxonomy for a manufacturing assembly task where a task can be divided by skills and then having skill primitives. These primitives can be a very complicated AI-based one, but still there is a taxonomy where you can go from bill of process to bill of materials to bill of processes and divide that into tasks. That requires still a lot of more research. That will be super useful to really mix this symbolic AI part of things to now the more hot data-driven deep learning approaches. Is extremely important to facilitate the explainability and how robots acquire these autonomous skills. This is another example from Kel Goering, or now the CIO at Ready Robotics, where that he proposed when he was at Johns Hopkins University. This was the start of the research that later on led to Ready Robotics, where he created symbols and predicates that can come from perception system, for example, but are then aggregated by a predicator, and then there's a behavior tree that unifies this information. Super useful to have, and this is how it looks today, right? In a product, in our Forge 5 operating system. This is one of our applications called Task Canvas, where a user can just go there, any user, right? This is very intuitive, and debug a program just by looking at it, right? With explainability of what is going on. This also has an added value of that the tasks created by users are explicitly labeled, and there is a structure. So then it's very easy also to later on run machine learning methods on top of that. So imagine if you had, that's another problem, right? That data today is very heterogeneous in manufacturing. Imagine if you had that across all robots, across all factories, that you really know that you have tons of examples of what a picking and manipulation example is. And it's not an end-to-end algorithm that is a black box, but well identified and data categorized. Wouldn't that be awesome? Okay, so just wrapping up in the next 3 minutes. I will talk about other roadblocks, apart from the 4 that you saw there. You know, data is siloed and heterogeneous. If you have been to no 2 factories look the same, system experimentation is costly, the manufacturing data is siloed. I think as a community also, we should do a better job on helping this process of having task labels, right? And understanding what is going on. For example, sometimes, yes, you get the vibration sensor of a machine, but what does it mean? Well, if you identify that with the context, you will see, okay, the door was closing there, so it's probably normal. So I would like to point you at some work that we presented at the AAAI Spring Symposium last year on how this data can be enriched with semantics to have more meaning. So last slide, some takeaways. Speed and precision at the system level are important in industrial automation. We cannot give that away just to achieve flexibility, right? It has to make sense. Flexibility has to make sense in the overall ROI of the system. The customer needs to get ROI. Successful picks is not necessarily important. Station throughput is an important KPI. We need to compare to existing approaches, not just, and really be careful of our messaging when we put that out there, right? We get a lot of attention in the news and it looks like, okay, reinforcement learning will revolutionize manufacturing and we are going to have, Amazon will not have any workers because everything will be automated. It still takes time, right? It takes time to, and it will take time. The same happened to other industries like self-driving cars. If you ask everybody 10 years ago, it was around the corner, it's still not there. We shouldn't follow those mistakes. We need to standardize ways to collect and annotate semantic data and find easier ways to contribute that data for R&D. Autonomous functions surrounded by good old-fashioned control provide reliability. Potential costly failures make it enormously difficult to implement AI-based robotics. A wrong pick, nothing happens. If you assemble wrong, if you put the wrong assembly on a product, it can explode sometimes. If you're assembling a battery, for example. The cost is much higher than having a wrong pick or a wrong item delivered. So that's something to be taken care, and that's why these systems are taking longer to be shown in real manufacturing, and that's fine, right? I think we should still continue to research on those topics. Industrial autonomy needs to be developed as a field on its own. Just take a look at the huge amount of industrial automation. And I don't think we do a good job on that in the US. If you go to see the depth of industrial automation knowledge in countries like Germany or Japan is amazing, right? And this is a field on its own. And industrial autonomy, I think, has its own peculiarities that needs its own field. Benchmark accelerate innovation. Last year in this conference, I gave an entire talk on benchmarks. I think still they are important. I don't think simulation benchmark, even though they are cool, they add any value in manufacturing. We can debate about that, but I think we need physical ones. And an open question, how do you test and validate an AI-based automation product, right? How do you, this is still an open question. It was an open question when I was at Siemens. It's still an open question now on how do we reliably test and validate all the potential cases that you have in autonomous scenarios, particularly because you don't know what you don't know. So that is the end of my presentation. I'm now open now and in the discussion, also later today, for any questions that you may have. And really happy and honored to be here. Thank you.
Great, thank you so much, Juan. We're just going to take a second and switch over to our panelist view, and I'm going to add my colleague Vin to answer any ARM-ish questions, and then you as well to the panel.
I will stop sharing my screen then.
So awesome talk. I was wondering, so you said you think benchmarks will accelerate innovation, but what do you think those benchmarks will look like if not in simulation? Like what physical benchmarks are you thinking of? Are you thinking of like test objects that you assemble and then you validate, or like you evaluate based off of that, or what?
I think this is a very good question. Right? It's clear there are things like OpenGym from OpenAI, very cool thing in simulation, right? But is there a similar thing? And that will be very specific, right? Probably we wouldn't have just the benchmark that governs all the benchmarks, right? We will have several ones. But for things like assembling cables, or for things like assembling connectors or pins, there could be ones like the one by NIST, right? There is a very good NIST board. Now, the question there is, that's what is very complicated, right? Because in the machine vision area, you can say, I'm better than this algorithm. But in the physical world, you have to define a lot of things, right? The performance, the robustness to perturbations, how well does it generalize if you place different components, at what cost, right? I can have a $1 million system that performs better versus I use whatever I have in my lab. Obviously, I will be more slower, but it's important to clearly identify those parameters. Also, the data that you use, have you used 2 days of simulations versus it just works? And what are the limitations, right? It's going to be much more difficult to compare 2 algorithms, but it will give a lot more openness into this area. And I still it's important to compare, right? To see, okay, I'm that good with this kind of constraints.
It seems that we're still waiting on some questions. So I had a question. So, some of the, like what you listed, for instance, with some of the aspects outside of manufacturing, right, that robots also will encounter. So I'm curious, do you think that we should start like robots for manufacturing and then coming over these roadblocks this way, or do the general robotics overcoming these roadblocks, which some of them happen in other fields like medical robotics, right? And then applying it to manufacturing. Which one do you think might yield the maybe better in quotes, result?
I think the unique thing in manufacturing is that you most of the cases you control the environment, and by controlling the environment, you already won a battle, right? Controlling a process is like, I don't know, like controlling a wild bull or something, right? So you need, or a wild horse, right? You need to tame it. It needs to be controlled, and you have a lot of also possibilities to define your environment so you are controlling that process. That doesn't happen in the outside world, right? If I am at home, I cannot really control if things are on the floor or if how ordered I might put in the dishes so I can load the dishwasher. Of course, if I find that let's put an example of loading a dishwasher, right? At home, this may take 10 hours. I don't care, right? What I care is that I come back from work and my dishes are in the dishwasher. That's my goal. Versus in manufacturing, this will be bad, right? If I want to automate, let's say in a restaurant, that my dishes are loaded and I have some timeline, the throughput is very important. So I don't know if one will lead to the other, because they have completely different conditions that surround them. And the fact that I have the entire model, that I can model in simulation my entire factory, this is really hard to get into the real world. So naturally, there will be different methods as they have different objectives. But there is a lot of, obviously, of cross-pollination that and learnings from one area can be applied to another. I hope I answered your question, Vin.
Yeah, no, that was good.
So we have a question from the chat from Fabio. What are the main limitations of current simulators that make them not useful for manufacturing?
Good question, Fabio. Thanks. So I think simulators are useful, but as any simulation, you need to know what are you using the simulation for, right? Am I using the simulation to, for example, assess the reachability of for the planning phase of my manufacturing, right? As you saw in the videos, I saw a video from Process Simulate. Amazing tool, right? Because you can define the reach of the robots, the throughput, and that works quite well. For a stochastic method, now I'm talking about a simulation. Those simulators don't work that well because they are built for fixed processes. Like I have a throughput, but what if that throughput is stochastic? What if modeling that curves is something that, but I think this is easy to address, and these companies are addressing them. One thing that is not necessarily good, at least the ones that are used for manufacturing, is to generate synthetic data, right? Which is used for a lot of. That is more on the research side of things. Still, even on that angle, contact dynamics are very difficult to simulate. I was talking with Ken Goldberg every time that we see a rocket out in the moon, right? How precisely you can be to put a robot on Mars. I mean, you can know it by the second. This is amazing. But just moving something in your table, it will be different every time. Like contact dynamics is like so difficult, right, to get it right, and that's also a limitation there, right? So you need to take that into account when you are simulating. But overall, I think simulators are a great tool. It's just it has its limitation. Nothing replaces the real world because there are so many nuances to the actual processes.
Okay, this next one's a much longer question from Lucas in the chat. One of the challenges in robotic manipulation is task specification itself. The tasks you mentioned are very diverse: pick and drop assembly, assembly packing, etc. What are your views on the different types of interfaces and the associated object/scenes representations that will enable goal/task specifications on this diverse set of tasks?
That's a good question. Thanks, Lucas. I think the two papers that I referenced were slightly into that arena. The difficulty is, where do you draw the line, right? Even if I say fastening, right? This seems like a skill. And you stop there, everything works. But then you go to real manufacturing, there are like million types of screws and ways to fasten a part. And then your ontology gets huge. And there are standards and ways to represent that. And that's the real world. We cannot simplify how complex the real world is and manufacturing and the huge amount of possibilities that are out there. But it can be hierarchical, right? At some point, they are all fastening, right? And they may have something in common. And when we are doing learning, it will be important that if you learn on a specific, to screw, for the lack of a better word, it can also apply to others, right? So if I understood the question correctly, it will be to, first of all, have a lot of hierarchies. And then if you are acquiring those skills from, let's say, a perception system, right? Having ways to map it, right? I don't know. For example, if you are learning from a human doing a pick and place, that you can also transfer that to a robot, and that will be the section that you are learning. Maybe you are just learning the placing part of things and not necessarily the movement of the arm. So categorizing and breaking it into smaller pieces as much as you want. And I hope I answered your question, Lucas. Otherwise, we can follow up offline.
So the next question from the chat is from Curtis. He said, you mentioned robots work, humans rule. And that for a lot of industries, that's true for a lot of industries. There will need to be a human in the loop to deal with edge cases. What do you think about the trends in end-to-end AI solutions, e.g. self-driving cars without drivers, only passengers? Are end-to-end solutions too risky?
I mean, in some sense, when we get into an Uber, we are in the hands of a really complicated neural network that is inside our brains, and we trust it, right? So that is on one angle. On the other angle, I still remember the first IEEE or one of Intelligent Vehicle. There was a conference called Intelligent Vehicle back in 2010. It was in Spain. I attended. And Chris Ursum, that was leading the Google self-driving efforts, now he's the CEO of Aurora, was presenting that, like how bad is that humans are still behind the wheel and that autonomous cars were behind the corner. And everybody kind of agreed, right? Next year, there will be autonomous cars. I will argue that we are 2021 and autonomous cars haven't even touched the life of any person. It hasn't made the life of any person better, apart from a lot of engineers that we are really getting good salaries because of that, and companies, right? And that's the truth, right? We cannot just so on that end, I think we are confusing being driverless by being humanless. I get a lot of value of my autopilot in my Tesla. It works great, but if something wrong happens, I'm still on the wheel. And still we are going to see that. There are so many edge cases out there that are difficult to control. And it will take some time until we master it. So for the time being, same thing for the robots. Now bringing that back to manufacturing. Okay, the world is Newtonian, right? So if you can leverage the laws of physics, and still, why are you going to throw the controller of a robot that works great just to have a neural network try to guess how to precisely place a part? Focus on the parts where modeling doesn't work. That is the context, right? This is very hard to get by modeling. Hey, let's do it. Let's use data-driven approaches and AI and ML and deep learning to solve that. So I see that, and really not under humans are amazing, right? Our hands are amazing, our brains are amazing. The context that we can give to a situation, right? We identify something is wrong immediately. That goes a long way. So having, also making, again, my point on having interfaces that are very easy to program for people to understand and really troubleshoot and enable them to own their destiny and not be that the destiny is part of a black box is incredibly important in manufacturing. And we are seeing it. Even COVID, right? When we needed the most the robots, right? Humans couldn't go to the workplace. We found out that robots were not up to the task, right? They weren't, right? And see also the cutting edge AI that you get with Alexa or with Siri when you ask something. It gets wrong sometimes, right? Doesn't matter if I said, where is the restaurant X to my Google Home. If they get it wrong because I have this strong Spanish accent, nothing happens. But if the robot is using an AI method or a machine learning method in manufacturing and I misplace a connector and suddenly my part breaks on the field, that has a lot of repercussions there.
Yeah, I think also the risk varies a lot based off of the situation. So you do have to do like a risk assessment, and the risk can be mitigated by, certain safety standards that people are working on. And, we might just not be at a place where we can trust human life in the hands of AI quite yet. And I'm not entirely sure we ever really want to be in that place. But yeah, it's just a matter of picking and choosing and running risk assessments.
Exactly. As I saw also the video on the recycling robot.
Yeah.
Full end-to-end AI. Perfect. I mean, it's better than nothing, right? What happens if you misplace a bottle? Okay, nothing happens.
Yeah. Our next question is from my colleague, Joe Falco. He said, simulating contact dynamics is tough. Who is working to address the deficiencies of robot simulations and physics engines?
Good question. Yeah, I would like to know that too. I cannot point you to Gazebo is getting better, right? There is a lot of nice work there. I cannot point right now to an excellent simulator in that area, but by all means, if someone knows one, I'm happy to test it.
There are some recently funded by the National Science Foundation reports regarding hybrid models using both physics-based and AI for certain contacts. One that I saw in particular was fairly recently, was actually in soft robots, using hybrid models for those soft robots, being robots made out of bendable materials. The dynamics of those are very, very difficult. So there is work done in the academic space. However, that's the academic space. maybe 10 years from now we'll see it if it ever comes out.
It will have an impact. That will be something that will really still one of the drawbacks of reinforcement learning is that it takes long, right? And there are tons of ways that you can accelerate it, but it's still in the real world with the variability, it may still take time, and time is money in manufacturing. Very good question, so thank you.
So I have one last question, and this is might be more difficult. So this workshop is on both AI for manipulation and on manufacturing. Manufacturing is pretty ill represented in academia. What can we be doing as people who are in both spaces to allow researchers to do meaningful work involving manufacturing, like basing tests off of manufacturing things, bringing things back to real application spaces?
Very good question, Megan, and really ties close to my heart, right? When I was 6 years ago, I had the task to work to, as I explained at the beginning of my talk, to come to Silicon Valley and really talk to the professors in this area and say, okay, can we make them work in meaningful problems that we have in manufacturing, being Siemens, right? And back then, and still in most cases today, deep learning, like most of the interest was in self-driving cars because that was the hot topic, right? Everybody was just looking into that. It's hot, money is there. I will get hired by one of these companies after that. This seems like to be so transformational. And I was trying to make the case when I was talking back then to the professors that yes, that's important if we will eventually solve it. But I will argue that there is a much closer horizon where we can impact manufacturing using AI. Manipulation is one area, but there are tons of other ways, right? You can optimization. Everything that is not real time will have a shorter span, inspection, detecting defects, optimizing your plant. That you can use data-driven methods and have an impact today. And as a matter of fact, there are many companies doing that. So what we can do better is, as companies, right, make the case to when we reach out to faculties that this is important. Also, this is a two-way, right, conversation. Be open to share data, be open to share problems, and be open to test things in the real world. I think institutes like ARM make a really nice work on bridging that valley of death between TRL 1 to 3 and TRL 7 to 9. This TRL 3 to 7, it's called the valley of death. Many things die. You see a nice video in your lab, and why don't you see it in manufacturing? Because nobody's taking the time to mature the technology, to nurture it, to make sure that it really works, right, in a manufacturing plant, at least in a representative environment. So leverage those institutes. Don't be afraid, right? Also, I think system papers are very underappreciated. Sometimes you just want to be a little bit better and then move on. But system papers are good because they saw a solution, right? And end-to-end. And robotics is about systems too, right? It's not just about algorithms, but how do you put this into something that works? A lot of cases also is about accessing to resources. Not everybody has a lathe and a robot that they can use, but companies should be more open also to share those resources, or at least as a national level to make them more available. And really, people still think that manufacturing is like a Bruce Springsteen song, like this depressing place that is dirty. It's not. It's like the coolest place to be right now. It's full of robots, where technology happens, where really cutting edge things happen, and where you can make a difference today. And so I hope I give some hints in this long answer, but it's really a two-way where there should be appetite on one side and push on the other. And as an industry, be more open, create standards, find a way to share more data and more real use cases, and things like ARM really help.
Awesome. Thank you so much. I think that wraps up the first speaker session. And I'm going to turn control over to my colleague, Clemens.
Hi, this is now starting for the second session. The first speaker in our second session is Danica Kragic. Danica is a professor at KTH. Danica, let me quickly set you to the presenter spot.
Thank you, I'm here.
You can share your screen if you click.
Absolutely, let me do that.
Let me finish that little intro. So Danica is a professor at KTH in Sweden. She directs the Center for Autonomous Systems. She holds way too many titles and awards for me to enumerate here.
Yeah, please don't.
No, I won't. And she and her research group have contributed over the years heavily in the intersection of robotics, computer vision, and machine learning, especially in manipulation and grasping. I remember a lot of great papers, especially in the area of deformable objects, dual arm manipulation, combining multiple modalities for manipulation, and so on. And today she's going to talk about representation learning for interaction tasks.
Thank you. Can I just ask you a question? I know that I have 25 minutes in total. Should I stop after 20 and open for questions, or how do you do?
Yes, the original, the thinking was 20 minutes plus 5 for questions.
Okay, so I'll do that. Good, excellent. So it's quite a number of people attending. Thank you for taking time and listening to me and of course other speakers. So just to give you a little bit of a background or the context in which we work, when I talk about interaction, I mean both physical interaction, grasping, manipulation of objects, physical interaction with the environment, but I also think about interaction with human, either than non-contact interaction or contact interaction. And there are many works here. I chose 10 papers that we've written since 5, 6, 7 years back on some aspects of open problems or the problems that we addressed in these 3 areas. And I would say that the red thread in these is, Clemens said, we are marrying methods from control, machine learning, computer vision, and of course robotics to address them. So I would say that early work prior to 2014 has been very much borrowing classical methods from control to address some of these problems. And then during the couple of 5 years or so, we have focused very much on exploiting learning and integrating then control methods with various types of learning methods to address these problems. Now, what exactly are we looking into? So we are very much inspired by human interaction with the environment and mostly upper body, 2 arms, and multimodal feedback. So we are very much interested in looking into how we can integrate, of course, range sensing and images, plus tactile force torque proprioception. And for those that are still looking maybe for a PhD topic out there, if you pick any of these images, I would say that there are no robots in the world that can do any of these in open-ended environments. And I think also that that's something that it's very interesting to discuss. I mean, despite the fact that we have been addressing these problems for very many decades now, if you look into the final row or the last row of the slide, really interacting in various types of media, such as water or oil, for example, or interacting with objects that are deformable, changing shapes, and so on. We still don't, apart from not having simulators, as just has been discussed, we don't also have some of the basic theories yet developed in order to be able to model this types of tasks. Now, why interaction tasks? I think I already said they are interesting from the control, machine learning, perception, human-robot interactions. They span over very many areas, and I'm interested in very many areas. So I think that for me, it has always been interesting to see what we can, how we can learn by learning what the advances are in all those areas and then make a contribution. But also for the purpose that the majority of human manipulation tasks are contact-rich tasks. And if you are to automate lots of the processes in even classical industry that have not yet been automated, we need to address contact-rich tasks. And of course, there are very many challenges with respect to contact-free tasks in terms of exchanges forces of energy that we have, as just has been said. Pretty complex contact dynamics, and that it's also very difficult to define what maybe task is and how to exploit both the task and motion planning, feedback control, integrate data-driven approaches with control approaches, and so on. But I would say that what is also very important is that we need to think about the real-time aspect of this. And rely on, of course, multimodal perception and control. What I also think is that what is very interesting and common for this is that we need to address common complex physical properties which are not directly measurable by any of the sensing modalities. Now, I've been in this area for 25-something years, and I usually say that I'm driving in circles. So what does that mean? Here are some of the areas and problems that I have been addressing throughout the years. And that relate to the aspect of interaction tasks in various ways: mobile manipulation, grasping, dual arm manipulation, in-hand manipulation, contact-rich manipulation, and so on. And without going into details on each of them, I will just focus for the remainder of the talk on how we also now shifted from studying these in the context of rigid objects to soft and deformable objects. As I said in the beginning, the red thread for our research has been and is state representation learning, and these are some of the scientific problems we address. For example, how we can define state representations or learn state representations that are relevant for the task and that also generalize over various types of tasks. To what extent we can make this embodiment independent, so it doesn't really matter whether the robot has 3 or 4 fingers or whether the arms have 6 or 7 degrees of freedom and so on, what can be transferred in terms of the learned representation. How then the learned representation can account for multisensory data. How we can address the problems in terms of continuous, active, incremental, and self-supervised learning, and to what extent these can be actually used in the context of these types of tasks. I already mentioned a little bit cutting across rigid, soft, and deformable objects, and how we can encode physical parameters beyond the shape. And to do that in our work, we combine analytic and data-driven approaches by using various types of kernels, priors, regularizers, latent space representation, and also, to some extent, the sim-to-real transfer. Now, to just give you an example of one of the recent tasks that we are very much interested in, it has to do with assistive dressing. So we look into the process of how a robot picks up a clothing item, defines an opening that would need to be then swiftly manipulated over somebody's head. And uses dual arm manipulation to do that. And, we humans do this every day, and we do it also in terms of assistant dressing frameworks, where we dress kids or elderly and so on. And in this case, the green head that is very static here. I think one of the challenges is what happens when this interaction starts to be even more dynamic. I mean, it is very difficult and challenging already from the perceptual perspective of just identifying the state of the garment, but then also how does the robot actually coordinate the dual arm interaction with the garment while potentially the target is very much moving. So scientifically, we look into global and local representations for finding the relevant state representation, as I also said. And then, as I said, classical control is not sufficient. We need to leverage recent advances from machine learning. And here are just two examples. The second publication here that I will talk a little bit more about challenges, what it means to, for example, do folding. I know that one of my PhD students will be talking in next session. Joanna is going to talk about understanding physical interaction with partially soft objects, dynamic learning dynamics for robotic food cutting. So I'm not going to say much more here. But this is also an important aspect, and I just have it here to say that learning representations for deformable objects, something like garments and clothing item, is very different from learning representation for partially soft interaction with partially soft objects. And we can dwell on this for and discuss why this is the case. But I think that we also need to be realistic of what information can be transferred between different types of tasks or different types of objects. And I don't believe that there is a unique representation that covers all sorts of or types of objects that a robot will need to interact with in a daily interaction with the environment. Simulators have been mentioned, and I think that this is also one of the challenges we are currently dealing with, the inability of actually generating maybe enough of the data with real physical robots, learning from small data sets and so on, and also the fact that there are many simulators out there, but that they have been designed with different topics in mind. One of our recent science robotics papers actually surveys this, looks into how various types of physics or physics-based representations have been coded in those simulators, and what types of problems in terms of interaction have been addressed by using different types of representation. So the point being that, dependent a little bit of what applications people work with, the simulators are very much tuned towards that particular application. There is no application which we can actually, or there are no simulators today which we can, let's say, easy use for both simulating interaction with, for example, clothing items and for cutting fruits and vegetables. We really need to spend lots of time in, let's say, designing tasks. So we also are interested very much in benchmarking approaches. In robotics community, one of the challenges is that most of the labs have access to very different hardware. So in relation to clothing items or deformable objects, this is one of the, I think, robotics and automation letter publications that we recently had. About proposing a benchmark for bimanual cloth manipulation. So what could potentially be tasks that are relevant of addressing, and what are also the assessment criteria that the community can use in order to compare types of representations or algorithms used for example, control. More recent work has also looked into rather complex objects in terms of more topological, let's say, aspects or representations. We look into objects that are complex in geometry, so objects that exhibit holes, but where holes are, for example, very important for fulfilling a specific type of a task. So apart from proposing a sequential persistent homology algorithm for being able to learn topological representations for predictive models of deformable objects and do a couple of different tasks, I'm just going to show what these are. We also use the same type of framework to, again, design a an environment, or several types of scenarios that can be used for, again, examining now in simulation various types of representations for non-trivial deformable objects. So this is also going to be presented during RSS in one of the tracks. So it builds upon PyTorch. And it's at GitHub for those that are interested, and it has implemented a couple of different scenarios that can easily be adapted to everybody's kind of like tasks or interests, what you're interested in. If you're not interested in backpacks or throwing a lasso or maybe putting a mask on a mannequin, you can do something else. But just to give you an idea of some of the tasks, we defined 3 levels of difficulty: putting a tube scarf over a mannequin's head, putting a mask over the ears, putting a backpack with long handles around the mannequin's arms. What we are looking into is how we can control the grasping, the motion of the grasping points so that the task is fulfilled. I think it's just interesting to see still how much effort it takes in order to be able to demonstrate something or to assess something that humans really do without lots of cognitive effort. It feels on daily basis, but still for assessing these on robots, we still have quite some let's say quite some challenges to address. Now, from the perspective of representational learning, as I said, we are also looking into methods that, as I said, are general from the perspective of that it doesn't really matter if the robot is tasked to drag a human from the water, pick up a bag, or perform some form of formation control. We look into how, for example, geometrical representations or methods can be used to address or represent these various types of tasks. And these are just a couple of examples where we address that. And of course, then probabilistic methods, and I'm going to say a little bit more in the final part of the presentation, what are those and how do we use them. Now, when it comes to deformable interaction, physical interaction with deformable objects, there are many tasks. Of course, we envision assistive dressing was one of them, but there are some one would consider simpler tasks, such as, for example, folding, unfolding, ironing, and so on, that might be relevant for a robot to address. Now, the problem, of course, is, in perception. The infinite dimensionality really of the observations make this problem of vision-based action planning rather difficult. So I wanted to give you an idea of a recent work that we are leveraging and results from machine learning. What is that we address? So the goal is to find a low-dimensional representation of a system for visual action planning. And we wanted to encode the relevant dynamics to perform in real time. That's why we need some lower dimensionality of the task. We wanted to reflect similarities between relevant state and also capture feasible transitions between states. So the system of then folding would have a start image and a goal image, and the idea of the visual action planning would be then to provide a set of states or images through which the system would need to pass in order to get from a start to a goal position, and then a set of associated actions. So we use, for this purpose, variational autoencoder, a very common model that is used for representational learning, but with some robotic-related, I would say, changes where the encoder is encouraged to map similar observations that correspond to different states further away using so-called weak supervision. So one of the big problems, if you think of the state, is if, for example, you would like to move from let's say having the left sleeve on the right one, or from the right on the left, there is really no single action that will bring you between these two states. Although these states might look visually very, very similar. So the idea is to take a couple of these representative examples and say that, well, there is no single action that can bring me between these two different states, and this is what we use to actually enlarge the optimization part in variational autoencoder with contrastive loss. Then the third part of the system is so-called latent space roadmap, so graph representation of then encoded or learned representation, which is a graph structure in that latent space we then use for planning. And the plan then generates a visual plan, a set of images that represent that traversed state space between the start and the goal image, and then the action proposal module that generates associated actions that the robot needs to perform in order to achieve or execute that particular plan. I know that I don't have too much time to go through all the details, but the interesting part, as I said, is apart from finding the structure in the latent space by using a graph, is also using the contrastive loss in order to then connect the relevant state in the efficient manner. And this is just an example. It's not sped up, but the system is fed start and goal position. It generates a set of all possible shortest path plans, starts to execute, and in this case we have Baxter using both the left and right hand. After the first action is generated, here you see the generated plan. The outcome is always then compared to the current observation, and if the current observation does not correspond to what is expected to be seen in the plan, then replanning is done online. So just to, it will do the folding. Now, we can talk about this for quite some time, what are the challenges and whether this was a relevant thing of doing and so on. But what I think is interesting is that we can actually demonstrate that the planning for this very high dimensional task can be structured in such a way so that it can be performed in real time. And then there are, of course, a bunch of things that we could extend on. For example, considering textured items, changing the geometry, if the sleeves are shorter, if there is potentially a buttoning that will affect whether we want the front or a back to be the main part on which we start, or from which we start folding on, and so on. And also, given that we can do folding, can we do unfolding? And for those doing grasping, unfolding things is much more difficult than folding, and I think that you understand for both reasons. So I think that there are still many interesting problems there. So can we just reverse, use the same graph, or do we need to find other types of representative states, because many more things can go wrong when we start to do unfolding. What I think is very interesting is when we do robotics research and solve some of these problems that cut across like motion planning and representation learning and so on. There are many other problems that we need to address and that are maybe more interesting for other communities. Two subsequent works that resulted from working on then visual action planning is our recent work on state representation learning with task-irrelevant factors of variation, where we looked into what types of models for representation learning are good if we want to, for example, address the problem of factors of variation that are maybe not relevant for the task. So, for example, it doesn't matter if the camera observed the the scene from the side or from the above, the representations should still be the same. The action generated should still be the same, and somehow the learned representation should understand that, so that the camera orientation, position, and so on is just irrelevant for that particular task. Another problem that also occurred and that we addressed, this is our recent ICML work that will be presented in a week, a new method for evaluation of learned representation called GeoMCA, where we looked into, again, how we can find a better method to say whether the learned representation is good or bad for independent of the task or downstream task we want to solve. And if we think about lots of the recent work in the area of machine learning and computer vision, values or evaluates the representation based on the downstream task. So we have a method that is independent of the downstream task, and that looks into both local and global properties of the learned data representation. Again, it's a recent ICML paper. It's on my Google Scholar, and for those interested, I can provide a little bit more detail. So I suppose I will stop here and open for questions, if there are any, in the next 2 minutes. Sorry for going over the time. Thank you. So I think, I don't know if I can find anything in the chat that is addressed to me. Here, what do you think is a good representation for deformable objects? Key points, deformation fields, then fields embedding. I think it depends a little bit, of course, on the task. It depends a little bit on the sensing. It depends also on the capabilities of the robot. Of course, I would like to say, well, there is a single representation that's good for everything, but I don't think that that's the case. I think it's extremely, what we learned, it's extremely difficult to to start with relevant representation if only, we have a difference in like uniformly colored or, for example, textured garments. So already that is a significant challenge. So I would say that, again, anything that is relevant for the task, and I think that then the representation also need to be assessed for a class of tasks. So maybe, ironing, assisted dressing, and things like that, folding might be having or sharing the representation, while, I don't know, tailoring or recycling does not need as detailed representation as those would. So it depends very much, I think, on the task. And then we have, I don't know if this was to me, simulating contact dynamics stuff. I think this was for the
I think this
speaker before, yeah. So I think I need to give the floor to the next speaker.
Yeah, thank you again. Thank you very much. If there are more questions, there's the session at the end, the discussion session at the end of that session. I think you will be there.
I will not be there because it's really late in Sweden, but I encourage everybody who has a question just to drop me an email, and I'll be happy to Zoom. So just drop me an email.
Great. Thank you very much, Danica. Bye. So then we go on in our program. The next speaker, we drop people. The next speaker is Parag Patre. Parag, are you here? Yeah.
Yes, I'm here. Just a mic check.
It works perfectly.
Awesome.
So Parag is a senior engineer at Magna International in Troy, Michigan. He focuses on advanced robotics, R&D, specifically in the fields of robotic perception, manipulation, and grasping, with the goal of advancing manufacturing technology. And today he will give a talk on grasping and manipulation opportunities in automotive manufacturing. The floor is yours.
Thank you. Thanks for the introduction. So yeah, hello everyone. Joining you live from Pure, Michigan, Motor City. My name is Parag, and what I'm going to talk about is the grasping and manipulation opportunities. The keyword is the opportunities, as I won't be talking about any solutions. Kind of here to also look for solutions, and looking at other speakers, I believe we have solutions out there that we can use. Before I go further, I thought some introduction about Magna is useful. It's not a very common household name like Facebook, Google, or even Ford, Tesla. So Magna is a tier 1 supplier. It positions itself as a mobility technology company. And when you have your OEMs like Ford, General Motors, or even Tesla, Magna is one of the biggest suppliers, which provides parts as well as manufactures certain sub-assemblies, and which then go into the final vehicle assembly. It is recently also in the space of all this driver assistance tech and the sensor packaging, and therefore that's where the technology piece of it comes into picture. It has a huge global presence. It's also a publicly listed company, so all of this information can be found on any of the stock websites. So $32.6 billion in 2020. And those of you who follow MGA, even during pandemic, it has done relatively well in this segment. Magna has presence in about 347 different sites, so 28 countries across the world, about 100 different facilities right here in North America. And the global workforce is 158,000 very hardworking people. And it's ranked #1 in North America and 3rd globally. So like anyone else, any other companies, obviously innovation is highly valued. We always assess the technology in terms of in which of these pillars it classifies or helps us to go further. So is it smarter, cleaner, safer, lighter, and affordable? So a lot of these AI technologies obviously have impact in all of this, as well as the advanced robotics aspects help us to improve our operational efficiency. And then they kind of factor in the affordable part in most cases, right? So that's how we will look at any new tech. In terms of what Magna produces and supplies, pretty much everything in a car. You have body and chassis. This is where you have the framing, such as your A pillar, B pillar. You see exteriors. All of us enjoy using the power lift gates, and Magna was one of the innovators in this field. The roof system, convertible roofs, powertrains, electronics. This is one of the growing areas, especially with the driver assistance systems and the self-driving systems that are coming out and are getting a lot of traction, even though we are not there yet. As well as electronic stuff in your car, such as your rear view mirror, front view mirror, and so on. Cameras, for example. Mechatronics, mirrors, lighting, LED has been one of the latest and greatest things in the car space. And all of us enjoy the comfort seating, as well as if you see the last circle, which is the complete vehicle assembly. This is another strength of Magna. Not only it supplies all these subsystems and parts, in Austria and Graz, we also have a complete vehicle assembly plant. And some of the cars which are popular, which you might know, are the Mercedes G-Wagon, as well as Jaguar I-Pace. These are some of the volume-produced cars assembled by Magna. Also, very recently, we saw this car by Sony, which was showcased in CES. That's also a niche production collaboration with Sony and Magna. So in short, Magna is involved in complete engineering and services all the way to the full system knowledge about a car. And this is where in this entire pipeline, there are lots of opportunities where we think advanced robotics as well as AI technology plays a role. So coming to my focus in this talk, it's the opportunities. My goal really is to talk about what's happening in manufacturing, what are the opportunities, and the biggest takeaway are basically it's a high volume production environment. The parts are always inconsistently presented, and we'll see some pictures and videos soon. And there are lots of variations that happen. They could be variations in the part shapes, sizes, color, texture, shininess. Some of them could be oily. And at the same time, all of this has to work very reliably. And reliability is the king when it comes to automotive manufacturing. There cannot be a downtime which is attributed to something that's coming from you. And there are certain liability issues that we need to keep in mind. So this shouldn't be any surprise. Anyone familiar with the modern car? There are 30,000 parts on average. This goes down all the way to the nuts and bolts. And this is the number of parts that go into making a single car. Many of these assemblies could be manual. Some of them are automated. There are huge welding lines which will do a lot of automation. But somewhere amongst all of these global sites, people are assembling them or feeding the parts. And this is where we have these opportunities for the next level of automation. Robotics obviously is not new to Magna, and a lot of us are familiar with all the pictures we see from Tesla or any other welding line where there could be hundreds of robots in a welding line doing weldings and working together. A lot of these implementations are what we call the old way or the traditional robotic deployments. Even within Magna, you would see under a single roof, there could be thousands of robots. And there is just one thing common to them. These are all handling fixtured parts. The parts are always coming at a known location, at a known pose. So they're not flexible. Even if the part moves by a little, it can stop the line. They are usually behind the fences for the safety reasons. And anytime you have to change the process or the part, this can be a lengthy as well as an expensive process. Getting rid of fences is also an important aspect because they do use up the precious floor space in your factory. And anytime you need to make a change, you need to go through a whole new risk assessment, make a new fence design. And these are things then, that play into like, okay, should I go with this automation or not? So these are kind of how the current automation, which is widespread within manufacturing in Magna as well as in other automotive. And the point is, from all the 30,000 parts we saw before, there is still a huge scope for automation. And this is where the parts are in unstructured environments. And just to show you case studies, this is from DoorTech, one of the subsidiaries of Magna in Canada. You will see an operator building a simple thing in the car, which is a door latch assembly. So that simple housing will consist eventually of 50 different parts which need to be assembled. And they all need to work together. The tolerances here will be really tight. For the human operators, this is relatively easy because they are able to just blindly dip their hands in the bin, pick up parts, and they feel their way around, and they are able to do the assembly and insertions. So video gives you a sense of just the number of operators who are involved in making something like a simple door latch that goes into car. Obviously, each car can have 2 to 4 different door latches, so the sheer volume of this product can be imagined. So it's in millions of per year. So this is a benchmark line, at least also for internally for us at Magna, that we look at as something to define the specs or define the technology packages that we need to solve to automate some processes like this, which have unstructured environment. They need perception methods, and as well as your tactile perception, force feedback, advanced path planning, and so on. And we think if we can solve this problem, we can then trickle down those pieces to other different problems within Magna. We talked about the unstructuredness of the parts, and this slide basically gives an idea of how a raw material will typically make its way onto the floor. And previous speakers touched upon that. If you focus on the left side of the slide, if we just purely look at just the nature of parts, you have parts that are darker. There are parts which are shiny, oily. Some of them will have hindrances. Basically, these are the plastic coatings or rust protection. There could be slip sheets, as well as they go from plastic parts to metal, light to small weight, and heavyweight, big, small. So that's just the sheer number of variety and how the parts come. A lot of times when you're picking parts from the bin, it's not just the part that you pick. As I mentioned, there could be those hindrances. So you also need to be able to detect some sort of a translucent or almost very less opaque or transparent plastic sheet, which sometimes even is a problem for even AI-based systems. And then that needs to be grasped, taken away, and then immediately the sensor still needs to be able to work good enough for the actual part, and then grasp those parts and so on. So that's the challenges on the pick side. If you look on the finished goods storage side, which is the right-hand side of the slide, parts can go back into a bin. They can be stacked. If you see the very center picture where I'm moving the mouse cursor, which may or may not be visible, these parts may have to be stacked at very tight spacing, as small as 1 millimeter spacing. And that's also a challenging task. You may have to place parts in pockets, which are there to protect your Class A surfaces. And so that also represents how do you manipulate around those extra hindrances here? How do you open up the pocket and detect where the pocket is? Is it empty? Or and once you develop this, you might find, okay, your tech package works for that family of parts. And then the question is, how do you then generalize it to do everything else? And this is where we see some of the opportunities for future AI-related work. Just to summarize what we saw so far, so processes, lots of processes will have tight tolerances. Everyone wants their cars to have very good finish, no gaps, good seams, and that goes all the way down to sub-components level. So the tolerances are one of the biggest killers and new challenges for anyone getting into this space, as well as the second item, which is the fast cycle times. So in order to do both, this is where you have competing objectives, and we see the new players are, when we work with startups, would be the first level that they need to cross. And we would work with them also to define these specs and prove out their technology. If you see the third bullet, which is high part variety, this is a challenge, but it's nearly not as much of a challenge as it exists in warehousing, where in a single bin, you may have many, many different types of parts. And at least within the automotive manufacturing context, this is not an issue. Typically, you would have the same type of part in a bin. And then the reliability is another aspect. Whenever we deploy a new tech package in a production line, even if the line stops for 1 hour or so, that can mean several millions of dollars of lost production. And this can have liability, and these are waivers or insurances that the integrator must sign up for when they take on these projects. And this could also be some of the roadblocks for a new player to get into a risky space like manufacturing, automotive manufacturing especially, because the reliability is required and it must be proved out. And this is where also within Magna, we can help out to do such pre-production validation and verification for your tech and before it goes into the production floor. We touched about parts. They can be shiny, oily, flexible. A lot of the 3D sensors that we have investigated in the market. Anytime you have certain specularity in the object, they seem to struggle, especially if they are using some sort of laser projector or some light projector. And that seems to be one challenge. We have seen recently new players who have come up with fusion of some traditional optical techniques as well as data processing using deep learning to still be able to reconstruct a good 3D point cloud even for such challenging parts. And those are some promising areas. From the sizes we talked about, you have variation from millimeters all the way to the really large body parts, side panels, and so on. We need such automation for raw parts handling, as well as if you only focus on the Class A surfaces, these are the surfaces where you cannot have any blemishes added after you have done your manipulation. So you have to be very careful in how the gripper is designed when you handle Class A surfaces. And then just the grasping itself can be a physically challenging process for such parts. In terms of the environmental conditions, again, I guess in most cases, people are familiar with manufacturing environments can be a little bit different than just an office environment. But I would say compared to people who are tackling the self-driving car problem, where the whole world is open, the manufacturing environment is somewhat constrained. You are under a roof, there is cells, there are walkways, and there are already a lot of safety rules in place. So I believe the self-driving car industry, whatever technology that's being developed there and being tested out on the open roads, the risk to do the same thing within a manufacturing environment is much less, and probably the rewards are equally high. I added also this temperature and humidity factor because at least in many cases, we did see people developing tech packages and then they have their entire software stack running on a PC, which might be IP67 rated, but may not support relative humidity beyond 75%. And so when you build up your product, you package it, you need to consider all of these environmental conditions, including humidity and temperature, which sound not so dangerous things, but are often overlooked. So at least within Magna and general trend we are seeing in manufacturing for the new robotic stuff, we are focusing on the adaptive part, which is ability to deal with inconsistency in part presentation, flexible, if you can handle multiple parts from the same family for the same cell, some dexterity. When you pick a part, are you able to manipulate while you make a move and do a force insertion? And then the collaboration part, we want to get rid of the fences. All of these are then measured against some KPIs, so cycle time, operational efficiency, capital, and so on. Just to give a current state of what we have been doing. So I'm specifically from what we call the Advanced Robotics Group within Magna here in Michigan. And about 5-6 years ago, we started this program to look into how we can take our manufacturing to the next level. So a lot of the manufacturing process, as we saw in the video, it relied on this human vision, feel, and the ability of the operator to plan the next steps and store a lot of information, remember the instructions, and execute the task. So equivalently, we are kind of taking that motivation and going from the human senses to finding the equivalent in the tech space, like vision systems and perception, finite state machines, path planning, and so on. This is an old video from 2015 when we started this journey. We focused on the same door latch parts. So these are parts which are 1 centimeter in size and basically unstructured environment using vision system. There is some path planning going on, as well as when the robot inserts the objects, it's like a press fit, and you need to rely on certain force feedback to make sure that the item is in place. When you assemble an object like a spring, there is also some complex motions it has to execute. And this was one of the early proof of concept that we did back in 2015. So going from such proof of concept work to the production floor, this is an example of what we launched in production 2017. The video has been changed for speed. That's to basically obfuscate the cycle time for the general world. But on the left, you can see the manual operation done by the operator. These are A-pillars that go on the left and the right side of your windshield. And this is a laser cutting operation. So the part needs to have a lot of holes and trims cut out by the laser. And within a factory, you would have hundreds of such laser cutting cells, which do similar operations on other parts. So this sort of operation for the operator involves separating the part from the stack on the left side, right side, and loading in there, as well as when the laser cutter has finished the operation, it needs to go on a poka-yoke for inspection. And we took the entire thing, and on the right is what the robot can do. So let me play that again. So on the right, we see the bins. So on either side, we have the left's A-pillar. On the right is the right side of the A-pillar. The parts are somewhat structured, but the bins can have them at 0 and 180-degree orientations. They are tightly stacked. The spacing between the parts can vary from 2 millimeters to 4 or 5 millimeters. So there is some variability in how the parts are stacked. There's also some roll, pitch, yaw. And the vision system needs to then very precisely locate the parts in time so that the robot can grasp it and then do the same operation. So this is something we had in production until the end of that program.
Park, just a short notice, because maybe you can quickly finish up, because the slot is kind of the 25
Sure.
minutes are over.
So I will very briefly touch upon ways to work with Magna. We are always looking for university as well as startups. So we are involved in many different early phase researches as well as startups. So there could be low TRL all the way to TRL 6 and 7. Again, if you have solutions or you think there are potential technologies we could use addressing this keywords here. And the pictures you see are our involvement with different companies in the past amongst each of these areas. Just to highlight, we even have the Da Vinci surgical robot doing some manipulation for those same DoorTech parts to see the capability, as well as some of the fenceless work that we have done. And as I mentioned previously, for any such thing, we would always start with a pre-production proof of concept, validation, and verification in the lab. We have few labs here in Michigan, as well as in Europe, which are engaged in these activities. And then the next phase is to go in the full high volume production. So I think that's the end of my talk. I have my email address for any further questions that will come up later on. Thank you. Thank you.
Thank you, Bharat. I think we can do the question part in the discussion session after the next talk.
Okay.
So remember your questions. Yeah, so maybe we go, thank you, Bharat. Maybe we go to the next speaker now.
Let me see if I can figure this out. Okay, and okay to share my screen.
Mm-hmm.
All right.
Looks good. So the last speaker of this session is Matej Ciocali. Matej is an associate professor of mechanical engineering and computer science at Columbia University, where he leads a great manipulation research group. I actually personally remember one of the first papers I read in the space of grasping and manipulation was his eigengrasp paper on low-dimensional representations for grasp planning, which was pretty cool. And what I value a lot in Matej has this broad expertise that spans not only algorithms, but also hardware and sensors. And I think this is kind of unique and places him at a very interesting spot research-wise to tackle this complex problem. Today, he's going to talk about design optimization, sensor development, and dexterous manipulation learning for multi-fingered hands.
Thank you so much, Clemens. That was such a great introduction. I really appreciate it. And guess what? I have some eigengrasps in my talk today. Talk about, you know, what Danny was saying about going in circles. It seems like I was certainly nodding when she was talking about going in circles. And there you go. Our eigengrasps paper, the first one was, I think, 2007. And here we are 15 years later. And I'll be talking a little bit about joint synergies again. And, you know, it makes sense in a way, though, because what I'm here to do today is to talk about research, our research on multi-fingered robot hands. And, you know, I think the field has just seen tremendous advances in the last half decade, many of them driven by machine learning and reinforcement learning on manipulation in clutter, in unstructured environments. But still, I would say that with a few notable exceptions, many of these results have been using either suction vacuum grippers, like Juan was mentioning, or two-fingered grippers. And I know in the audience, for example, I noticed Andreas ten Pas, who, you know, pioneered the use of machine learning for unstructured pick and place with a parallel gripper. You know, and we have hands, we have multi-fingered hands. You know, people have been building this wide spectrum of hands, all the way from, you know, 2 fingers, 1 motor, all the way to the super complex shadow hand with 5 fingers, more than 20 motors. You know, why is multi-fingered dexterity lagging behind in academic research? I mean, there's obviously a question there. Maybe it's just not really needed for a lot of the things we care to do. Juan was also making that point earlier that, you know, he thinks there's still just so much we can still do, so much fruit to pick, you know, both figuratively and maybe literally too, with parallel grippers. You know, is there a place for multi-fingered dexterity? Is there a need for multi-fingered hands? I was very interested, you know, following Parak's talk very carefully, looking for opportunities for multi-fingered dexterity. So the first question, you know, is there a need? In academia, we have the luxury that we don't, you know, we can also work on things that are intellectually cool without being driven by an immediate need. So maybe even if there isn't a need tomorrow, we can still push ahead. And then the corollary question is, well, why is multi-fingered dexterity so hard? You know, is there a need for it? But also, why is it so hard? And I'm arguing that when it comes to multi-fingered hands, all of a sudden, all of these aspects come into play. We're talking about the kinematics, which, you can have all kinds of kinematics in a multi-fingered hand. It's not a parallel jaw where, they have to oppose each other. Actuation, how you actuate your kinematics. Sensing all of a sudden becomes very, very interesting. You've got all of these degrees of actuation. You want the sensing that goes with them. And then, of course, planning, learning, teleoperation. So all of these components, all of them difficult by themselves, and then the interplay between them, just so complicated when it comes to multi-fingered hands. And one question we've been fascinated by in our lab in the last years is, out of all of these places, where does intelligence live? And sure, it lives in the brain at the computational level, in, the planning and the learning, and that's what we're used to. But is that really the case? Is it really the way it has to be? And, again, looking at the decade, the results of the last half decade, we've had remarkable results, many of them with model-free reinforcement learning, but not only. Andreas's work, the original work, was with supervised learning, self-supervised learning, and now lately we're seeing a lot of work with model-free RL, focusing specifically on the computational level, and, learning policies, learning controllers. And one of the questions we've been asking in our lab for the last couple of years is, we have these very powerful optimization methods, because ultimately, deep learning, reinforcement learning, they boil down to optimizers, very, very powerful optimizers. Can we apply these to hardware? So the first project I want to bring attention to today is our work on using policy optimization on hardware. And this is work that was led by Tianjian, who recently graduated from our lab, and by Zhanpeng, who is in the audience today. And let me quickly, if this is, I'm sure many of you are intimately familiar with how policy optimization works, but please bear with me. I want to build this from the ground up. So please bear with me if these are things that you already know very, very well. So what is policy optimization? Policy optimization is the goal of deriving a computational policy that takes as input observations from the environment and produces actions. And the actions typically are in the form of motor commands that are then sent to the robot, and then the world evolves and moves to the next state. And this computational policy is usually expressed as a computational graph. It can have any structure you want. So for continuous control tasks, people usually employ a multi-layer perceptron for their computational policy. If there's vision input, there might be a CNN as well. But in any case, the computational policy is often expressed as a computational graph. This computational graph has a number of parameters that many of you know very well, the weights and the biases of the neural network. So then ultimately, the goal of policy optimization is to optimize these parameters, the weights and the biases, such that the action serves the desired purpose given the observation. So this is vanilla policy optimization. And what the field has found is that oftentimes these algorithms, they need so many training samples that they cannot really train on real hardware. They need to be trained on a physics simulator. Generally, a general purpose physics simulator treated as a black box. And there was an interesting, discussion in Juan's talk about, the limitations of such simulators. But still, even training in simulator, I think a remarkable advance in the last 5 years has been to show that you can train in a simulator, and then via domain randomization, you can still apply the resulting policy to real hardware. But in any case, for many of the results we've seen, training is done on a simulated robot. But interestingly, this simulated robot, includes all the hardware components of the agent. All the hardware, the body of the robot itself and all of its hardware is external to the policy, is not part of the optimization. In many, many ways, the hardware of the robot is considered to be part of the environment and not part of the agent. Which, us as roboticists, we like to think about hardware and software together. It doesn't really make sense. The hardware is part of the agent. It shouldn't be part of the environment. So the work that we did, what we call hardware as policy, was to say, look, what if we take some parts of the robot hardware and take them outside of the general purpose black box physics engine and simulate those parts separately? We simulate them ourselves, and we simulate those in a way that lends itself to auto differentiation, namely also as a computational graph. Can you simulate hardware as a computational graph? And of course, the structure of the graph is dictated by the physics of what you're simulating. And it turns out that at least in some cases, yes, you can simulate hardware as a computational graph. So let me give you a very concrete example of what that looks like. And in this case, the first problem we applied this to was we are optimizing the transmission of an underactuated robot hand. We start with a lot of givens, a given that we have specific kinematics, 3 fingers, 8 joints, and we'd like to have a single motor driving this. And the application domain for this is manipulation on NASA's Astrobee robot, which is very small, so you cannot fit a lot of motors inside a hand. But ultimately, the method is more general than that specific application domain. So we have 8 joints driven by a single motor. So that one motor is driving all of those joints via a network of cables, a network of tendons. And in the sketch on the right, the tendons are depicted in red, and you see a single actuator pulling on 3 tendons, which in turn drive all 8 joints. This is a transmission. It's an underactuated transmission that converts motor force into joint torques. And what's interesting about this transmission is that its behavior is governed by a number of design parameters. What are some of those design parameters? For example, the radii of all the pulleys that the tendons wrap around at the joints. Those are design parameters. The tendons can only pull, they cannot push. So restoring forces are provided by springs. Those springs have stiffnesses, they have preload levels. All of those are design parameters that influence the behavior of our transmission. And they are all very concrete physical things like pulleys and springs. So with this picture in mind, if we now go back to the idea of hardware as policy, if we take just the transmission part of the hand, the one that converts motor forces into joint torques, it turns out that we can simulate the behavior of this transmission as a computational graph with a very specific structure dictated by the physics of how tendons work. And that transmission has a number of parameters like pulley radii and spring stiffnesses and so on. And you notice now what I'm going with this in that the hardware policy here, the transmission, is conceptually beautifully similar to the computational policy. It takes in an input, it produces an output. In our case, the input is motor commands, the output is joint torques. Its behavior is governed by a number of parameters, and we can simulate this in a way that lends itself to auto differentiation. So now, if we redefine our action to consist not of motor commands, but of joint torques, we have this combined hardware and software policy that we can optimize together with the joint gradient propagation. We can compute a gradient of our redefined action, which is joint torques, with respect to hardware parameters, also with respect to policy parameters, to software parameters, to weights and biases of the computational policy. Because everything is auto-differentiable, so our gradient can just flow throughout the entire hardware and software combined policy. So now what we can do is we can optimize the hardware design parameters and the parameters of the computational policy together with any method that uses a policy gradient under the hood. So you can take your favorite policy optimization method off the shelf and try it and see how well it works on this problem. And in our case, the underlying RL algorithm we used was TRPO, and we're optimizing the computational policy and the hardware policy together. And it turns out that it is much, much more efficient than using any alternative methods that are gradient-free. For example, evolutionary strategies that are gradient-free. So if you have this full gradient, you are much more efficient in this joint optimization of hardware and software. And then beautifully for us, the remarkable results from other groups on domain randomization still apply. You know, we can domain randomize, and then we can take the resulting hardware policy and implement it in real hardware. So here you see the optimized tendon pulley radius resulting from the optimization built into physical hardware in a real hand. The springs that you see here providing extension, their stiffnesses and their preload levels are the ones resulting from the optimization. And then it works in the real world. Let me skip forward. So here is we are using the computational policy and the hardware policy together. The computational policy is in charge of positioning the wrist and on deciding when and how much to close the fingers. And then obviously the hardware policy takes it from there and produces torques at the joints. So this is one example, but it's really, I feel we've just really scratched the surface. You know, hardware and software co-optimization is not a new idea. It's been around for a while, and it's potentially very, very powerful. And we know that in natural evolution, hardware and software evolve in this beautiful symbiosis, one for the other and with the other. And all these new developments that we've had with fantastic, stable multi-body physics engines, with sim-to-real transfer, with cloud computing, and with model-free deep RL, all of these are coming together for really a golden age for hardware and software co-optimization, which, you know, hopefully we're just at the beginning of. And here's another example. Here's another example going back to synergies. And this is work that we're doing right now. It's very, very active work. Synergies are patterns of coordination between joints. And again, not a new concept by any means, both in kinesiology and in robotic manipulation. But we think that this new perspective allows us to have new ways to discover such synergies, right? In the previous work, we assumed that there is a single motor driving 8 joints. But wouldn't it be better to automatically discover how many motors you need and which joints each motor needs to be connected to? And this is what we're working on right now. This is very, very active work led by Zhanpeng. And what we're trying to do is, given a robot hand and the number of joints and a set of manipulation tasks, what we'd like to do is simultaneously determine the set of synergies that enable task completion and also optimize the control policy that uses those synergies. So this hasn't been done before because in the past, either you had a working controller and you were analyzing it to see if it uses synergies, or you already had the synergies and you are looking to see if you can come up with a controller that uses those synergies to do whatever task you want. What we're trying to do now is do both of these things simultaneously, come up with the synergies and also the control policy that uses those synergies simultaneously. And there's a bonus, right? I mean, why are people looking for synergies, for joint coordination patterns in robot hands? And they're interesting because they simplify control, because they might allow better portability of controllers to new tasks, but also because if you can realize synergies in hardware, then you can potentially build under-actuated hands, which could be a very, very powerful paradigm. So the way Zhanpeng is tackling this problem, he is training a combination of task-dependent software policies. So there's a software policy denoted by pi. Those are pure software policies for each task, all of those policies produce output in a low dimensional action space that then goes through a synergy model to be converted back to the full dimensional action space of the hand. And the synergy model is shared between all the tasks, right? Because we're looking for a set of synergies that enables a set of specific tasks. And what's interesting is that we can also put some constraints on the synergy model. You know, what does that synergy model look like? It can be a couple of interesting things. We can force it to be linear. Let's say we are looking for purely linear synergies. And in that case, the results are comparable to what you see from PCA. But we are optimizing the synergies with and for the tasks, whereas PCA can only look for synergies in a controller that already exists. Or going back to our hardware as policy approach, we can try and force these synergies to be realizable in hardware. And then we can potentially use them to build underactuated hands. Let me show you a couple of examples. These are brand new. This is very, very active work. I got these videos from Jean-Pong hours ago, literally hours ago. So this is the shadow hand, 20 degrees of freedom, using just 6 linear synergies to turn valves going from 0 handles. The previous one had 0 handles. This is a valve with 1 handle, a valve with 2 handles. And then finally, you'll see it turning a valve with 4 handles. So, and it's 3 handles, sorry. So 6 linear synergies enable all of these tasks. Interestingly, what we're seeing so far is that 4 linear synergies don't. If we're just trying with 4 linear synergies, it does very well at a number of these tasks. It doesn't really succeed at the single handle. It gets sort of stuck. It can't really figure out how to get it, slowly gets it all the way around with just 4 synergies. It does the other 2 tasks quite well. The 2 handle and the 3 handle with 4 linear synergies. If we allow the synergies to be non-linear, this once again enables all the tasks. So, this is, again, there's still a lot of work still to do here. And, we're pushing ahead, but we think that this could potentially be a very, very powerful tool. So ongoing work. Okay, so with that, let me switch gears. There's one more project I want to talk about. I'm almost out of time, but there's this one final discussion that I want to have about tactile sensing, because so far, we've been focusing on one end of the spectrum where we're looking at very highly underactuated hands, very compact, limited sensing. A lot of the intelligence goes in the kinematics, and we're trying to optimize the kinematics to behave intelligently. At the other end of the spectrum, you have these fully actuated multi-fingered hands, which can be highly sensorized. So give you an opportunity to also put intelligence in the computational components. And we're building a couple of these. We have a 3-fingered, fully actuated sensorized hand that has tactile sensing and proprioception, and then also a servo-driven 4-fingered hand, which only has tactile sensing. It doesn't have any torque sensing. We're playing a lot with both. The tactile sensors that we have on these hands are our own, we call it the disco finger, distributed interleaved signals for contact via optics, of course. And I'm not going to go into details on the disco finger because I've presented on it quite a lot in the last 2 years. So I don't want people to keep seeing the same presentation again and again. Under the hood, they have lots of LEDs and photodiodes. So whenever the finger makes contact with anything, we're getting a lot of light transport signals changing. So the interesting thing about the disco finger is that it gives you a lot of information. It has roughly 1,000 signals that you get from the finger. So whenever you make contact with the finger, a subset of that 1,000 signals will change. And then there's a lot of information about touch. So there's a big question there about how do you extract information out of that very, very rich signal set. And really there's two things you can do. So our raw tactile data is 1,000 signals coming out at 60 hertz, it's impossible to make sense of just by looking at it. It's just, mumbo jumbo as far as the human eye is concerned. But with machine learning, there's a lot you can do. And there's really, there's the supervised approach and the unsupervised approach. In the supervised approach, we collect training labels for our tactile data. The way we get our training labels is by poking the tactile finger in very controlled fashion. So here, the finger is being poked by a UR5 with a linear probe and the load cell at the end, which allows us to collect very precise labeled tactile data, and it's labeled with the location of touch and the amount of normal force that we are applying. So we have those labels, and then of course we can train a supervised model, a regressor or a classifier that will then output touch location and normal force, which is shown here. And then if you have that, so you have this supervised tactile model, so then you can take the things that it outputs, like touch location and normal force, and use them for things like model-free reinforcement learning. This is work led by Gagan and also by Max, who also recently graduated from our lab. And what we're using this for is to learn in-hand manipulation via finger gating. We have a poster right here in this workshop in the upcoming poster session, so please check it out, which is why I don't really need to talk about this too much, so that you can go and check out Gagan's poster and he will give you all the cool details. At a very high level, what we're doing here is we are learning in-hand manipulation with finger gating using only intrinsic sensing, just tactile fingers and proprioception. There's no assumption of known object pose. So then what we're doing is we're learning policies to rotate the object around the cardinal axis. Whatever object you're holding, the hand is trying to rotate it around X, Y, or Z. We're learning separate policies for each axis. And also, very importantly, we're not relying on external support. The object isn't resting on anything. It's held purely by the hand, which makes the system very unstable. As soon as you do the wrong thing, the object falls away. It's a very unstable system. And we have found that this really hinders exploration in model-free RL. So Gagan figured out that this can be addressed using an appropriate initial state distribution, and I will let him give you all the details at the poster session. This is what it looks like. This is an example of rotating an object around the z-axis. Some objects are easier to learn to rotate than others. So here it's rotating a sphere. Here's an example of rotating a cube. It takes way longer to learn, but it does learn. We're finding, we have initial results that the policy learned on one object transfers quite well to another object, which we're very excited about. Right, so compared to previous work, so this is the remarkable work from OpenAI on dexterous manipulation using the shadow hand. And that was a piece of work that I feel honestly, that it to me, that was a watershed moment, right? And I hope that more people see it like that, because there was a dexterous hand doing something that with model-free RL that I wouldn't have known how to do otherwise. So that was just remarkable work that inspired us a lot. Almost done, I promise. But the difference with what we're doing is that we're learning policies that transfer between objects that don't use any external sensing. So there's no mocap, there's no lots and lots of cameras or anything like that. And also we don't need intrinsic stability. Our policies work palm up, palm down, because you don't need the object to rest on the palm. You're holding it stably in the hand at all times. And of course, they did it on real hardware. Amazing work. The sim-to-real is fantastic. We're hoping to also achieve sim-to-real here, and that's very much work in progress. So hopefully, in the next couple of months, we'll have something new. And also, please check out our other poster also in today's workshop, which is Emily's work on unsupervised learning. We'd very much like to see if we can use our tactile fingers in unsupervised or self-supervised fashion. How can we learn an interesting state representation using unsupervised or self-supervised learning, very related to Danny's talk. And we're also using autoencoders But what Emily has found is that these variational autoencoders or regular autoencoders, they work much, much better if you also provide them with some context. If you are learning not just an autoencoder by itself, but you are learning an autoencoder and a forward model at the same time. And that really provides the context to the autoencoder on what it needs to learn. And I will let Emily give you all the quantitative and qualitative details on how this context training works much better than just training an autoencoder all by itself. And we're hoping to use that for learning actual manipulation tasks in the future. And yeah, this is finally it. And I'm just going to leave you with this question, which is, where does intelligence reside? At which of these levels? We believe that it can reside at all of these levels. And that's, you know, how we're going to get really cool advances. And hopefully, who knows, maybe we'll find the amazing applications for dexterous multi-fingered hands, in addition to the really cool work that's being done constantly on parallel grippers. A huge shout out to everybody in the lab. I've mentioned some of the folks leading the work here. And sorry for keeping you just a little bit longer. And thanks a lot for your attention. I'm gonna try to stop sharing. Thank you.
Thank you, Matai. I think we can now directly dive into the panel session with the questions also regarding to your talk and the talk from Parag. So let me quickly switch to a different layout. I think I can drop you in that panel session here, and I will add also Parag here. If he's still there, I hope so. Yeah, so maybe, yeah, if anybody in the audience has a question, please either leave them in the chat or click on this little orange bar here, and then you can take your spot. Maybe I just start with a little bit with one question that is directly related to Matai's talk. Basically, this joint optimization of hardware and software. And this, to me, seems like a perfect match to automation and manufacturing problems, where there's, and please correct me, Parag, or other people who are more in that space and have much more knowledge than I do, but I feel there's always this boundary between what part of the solution to use a design and form of hardware, certain tricks that you include, and I wonder, this paradigm, how have you applied it in your research to more manufacturing-like or automation contexts or problems beyond this? Or do you have any ideas about that? Or are there any inherent limitations that you see?
Thank you. I think that's a great question. And I think I agree that the fit is good, because these methods that we're using, they're very task-driven, right? You're optimizing a hand specifically for a set of tasks. And you have quantitative measures of how, and you're optimizing not just the hand, but the policies as well. So you're jointly optimizing the hardware and the software for a specific set of tasks. And so far, our tasks have been inspired by the NASA domain manipulation on board the International Space Station, but we're always looking for other application domains and other tasks. And, you know, for a long time, I think as a field, you know, we've tried to design hands. And how do you ensure that they're general? You can't really, other than trying to make them human-like, saying, no, a human-like hand, the human hand is very versatile, so maybe if we make our hand anthropomorphic, it'll also be versatile. I think it would be great to have these tools that allow you to specifically design a hand for a given set of tasks. And, you know, us as researchers, we're always asking what those tasks should be. I was very inspired, Parag, by, you know, for example, your example of the door latch assembly. And I was thinking, there you go, that's an example of a task. And of course, singulating complicated objects from bins where they're very cluttered. And I enjoyed those examples too. So for us, the presentations, like products are very, very useful to get those kinds of ideas of tasks. There's a big question of, how well can we simulate them? But I'm confident, tying into what Juan was talking about earlier, that especially with domain randomization, there are many tasks like, the door latch assembly that we can do a good enough job simulating that then domain randomization will allow sim to real transfer. I don't know, Parag, what are your thoughts?
Yeah, I think at least for us, whenever we are evaluating a new tech, it's maybe we don't get so excited upfront what's a new piece of new research or something is there. We are looking at the KPIs, and it's at the end we are looking whether it solves the problem and so on. So whether you use learning methods or other approaches, we will measure against our test bench and the criteria. But at the same time, I think we also realize we cannot hard code a lot of different approaches. We need to develop those general purpose approaches, which will then play into the scalability, right? We need to automate for thousands of different subparts. But anyway, I think I even lost the initial part of this question, so I kind of went into a different direction with this answer. Looking at some of the questions here in the chat. So,
yeah, let me maybe. One other question for understanding. You mentioned KPIs. What does that mean? I have no idea.
KPI is just the key performance indicators, right? So, for example, in a manufacturing setting, whether you go with approach 1 or 2, you will have certain success criteria. Your cycle time, cost, ROI, reliability, and so on. So all of those things need to be proved. We need to see the data. And especially when things go in this high volume production where you're making millions of these parts in a year, we need to see where things stack up. So
I guess part of the difficulty there is that many of the learning-based solutions or solutions from academia, at the beginning they won't do the task at all. Then they'll do it, but the KPI is going to be abysmal, right? It's going to be doing it 200 times slower than the human. So it's just having the confidence to kind of stay the course and say, okay, yes, it's incredibly slow now, but 2 years from now it could be faster. And how many technologies get abandoned somewhat along those lines.
Yeah, and I think this is where we also keep an open mind, right? So depending on which phase or what stage that research is, it might show promise now, and we need to kind of see ahead where it will be in 2 years from now, because some of them may have challenges from just the computing, and we know that those challenges will go away. Or just to give an example, right? So just we have to look at the core piece and then extrapolate where we see. And then in these cases, we will also, to use the word nurture, so work with the academic researcher or a startup to take it further and see if we can cross that bridge, go from the low TRL to the high TRL. And that's the approach we have been taking.
Mm-hmm. Maybe I just read one question from the chat here from Michelle Breyer. Parag, the plastic and metal parts seem very challenging for perception systems. What sensors are you currently evaluating for working with these objects?
Okay. Yeah, that is indeed, they are very challenging objects. And whenever we are approached, we do have our own test set of parts that we would evaluate them against. Obviously, in the field of deep learning, there are a lot of data sets and so on. Similarly, for our own internal evaluation, we have our own suite of test objects. The sensors we are putting in the production use, they are still off the shelf, nothing special, because we want the supplier to be behind the product, right? At the same time, we do evaluate some early stage sensors, which are specifically being designed for such tasks. I cannot disclose the names because we are still working in a stealth mode, let's say, with those different vendors.
Okay, thank you. Maybe a follow-up question here is also for Parag from Arsalan. What is a good criteria for assessing whether it makes sense to deploy a more generic learning-based solution, or it can be solved with traditional custom machinery that is designed for the specific task?
Wow, that's an interesting question. I would say, and this question will come up a lot of times in any application we do. Even for the door latch example that I showed, there are already methods out there which can solve that problem. And it will be done in a very task-specific way. And we know that. But at the same time, we are looking to learn from this and see how we can go from just the door latch to something else. So I think this is where, when it comes to that scalability aspect, right, we are not limited to just these 5 parts. We want to tackle all 30,000 parts in a car. So it will be really hard to do this custom policy or design for each and every part. So I think that's where we are also chasing such generic solutions. If I can teach a hand to grasp, manipulate on its own, that's ideal. So we do see value also in the long term for pursuing such research.
Thanks. A follow-on by Daniel Grollmann. Are you looking for systems that can work wholly autonomously, or would hybrid human autonomy systems be acceptable? If not, why not?
I'm assuming that question is also for me. This is case by case. There are places for robots. So typically in Magna, we would say anything dull, dirty, dangerous. These are the tasks for robots. And if we can automate or use robots for these parts and keep the human for other parts, that's a good combination. So there is no hard and fast rule. Again, it will go back to what is feasible. Does it give a good return on investment? And if the tasks, there are other pieces when these things go in on the production floor, which are maybe not so important from the research community point of view, but just from the people on the floor, it's how easy such a system is to maintain. Can they learn something? How good is the user interface? These are like simple things, but they make a huge difference in how well this technology can be adopted on the shop floor.
So, Parag, if I may also quickly follow up on this, I'm also curious about how often these tasks change. Right, once you have a specific step in the assembly, I assume, I mean, then it stays the same for years and years, right? For as long as a specific model is in production, right? Or do you have more faster changes than that?
Yeah, that's a good question. So this depends from line to line and what's being done. I would say in the past, and even today, once you make a model, you keep making it. Let's say, Model T was one type, one color. Now, everyone wants to customize different options in the car, right? So there is some level of customization. And just to give an example of a paint line, the conveyor belt is always moving. And depending on what's the volume of different color, blue, silver, you need to keep changing what gets painted on. And so there is, and again, this is a paint line example. We look at the door latch, probably for the next 2 years, it will be the same thing it will keep doing. Also, when you go to the body and frame parts of the car, these programs can go for 5 to 7 years without changing anything once the line is up and running. So in many cases, I would say there is not much of variability in the process for some of these. And in some aspects, there could be day-to-day slight changes that you do. So.
Another question that it's also for Parag that I have is, when you look, you mentioned before that you sometimes look at academic research to be used in your, how often does it happen, or in what sense do you look at what's coming out of academic research, or is that quite independent, or in that sense, if there's not so much relation, what maybe are particular assumptions that you would like to see in academic research to be more included or tackled?
I'm going to do my best to answer this. So we do have, as I mentioned in one of the slides, different ways we engage. And one of them is a big university research collaboration program. And that's just the corporate R&D in Michigan. I'm sure across Magna, different divisions engage directly. And there is, we do have, resources involved in this scoping, finding places, figuring out the mechanism, which are like the legal aspects, contracts, who owns the IP, can they have papers publishing, where the things go, can it be open? So all of these things, there is a mechanism that's evaluated. And I don't know if that was exactly the question, but we are here, and there is active focus to work with universities, and that's across everything. That's not just robotics or AI. This is also everything that's coming up: electrification, drivetrain, and all the other new stuff in materials. So university engagement is pretty high.
Mm-hmm. Yeah, no, the kind of answer is, my question was motivated by the fact, the workshop is a bit about that distinction between academia and industry, and maybe, the fact that in industry, maybe certain problem assumptions are very different from academia, where you can be very free in defining your problems. And this is one part of the contribution in academia, whereas in industry, there's, you have to deal, I guess, more with more constraints that are given to you of existing production lines and so forth. But thanks. Any other questions from the audience? There's one for Matej. Some of the results for dexterous manipulation were trained in sim only and deployed in sim. What is needed to make it work in real world? Do you assume you do system ID for the real hardware to fill in sim to real gap? If so, how sample efficient is it?
Great question. And I think we're going to be playing the same game that everybody's been playing for the last couple of years, which is you do system identification the best you can, and then everything that you feel you don't really have a good handle on, you do domain randomization. And again, if you look at the original OpenAI paper on doing manipulation with the Rubik's Cube, there's a wonderful little section on system identification, and they did a terrific job of it, right? And they looked at things that you don't immediately think to look at in terms of latency for action spaces and things like that. So yes, we're doing as much sysid as we can. We're quietly confident that we're going to be able to get it to transfer. Also because we feel that tactile sensing lends itself to transfer better than vision. We also have a nice noise profile on our tactile sensors. We know a lot. Because we've collected this very extensive labeled data set on our tactile sensors, we have a good noise model. So we're going to simulate that noise model, which we hope is going to go a long way. There are still some big unknowns, especially with regards to the underlying position controllers, right? The motors, the servos are position driven, they're dynamic cells, and to a large extent, the underlying controller is a black box. So that's what we're a little bit worried about, especially things like stiction. and we're actively working on it. We'll see how it goes. We're confident, but we don't have it yet.
Another one by Banti Gineti. A question for Matai. Optimizing hardware with tactile sensing seems very powerful, but there are many tools for optimizing software, including hardware, usually cameras as part of the environment. What is needed for optimizing hardware to be more accessible?
That's a good question. In terms of optimizing software, including cameras, I'd appreciate any pointers you have to specific pieces of work on that. We've been focused a lot more on hardware in terms of links and actuation and kinematics. We're thinking now about optimizing hardware in terms of tactile sensors, like you're saying there. But any work that optimizes software and hardware and cameras in particular, I'd love to take a look. So if you can send me either through this or any other email, and I'd appreciate a conversation on that. For us to make optimizing hardware more accessible, again, it boils down to how well you can simulate it. We know now that you don't need to simulate it perfectly thanks to domain randomization. How well you can simulate it, and then for our specific method for hardware as policy, we care a lot about simulating hardware in an auto-differentiable way, because then you can apply this much more powerful gradient-based optimizers. And obviously, anything is differentiable via finite differences, but that's not a very good gradient. So, there's a lot of very interesting work right now on general purpose auto-differentiable physics engines. There's work at Rutgers on that. There's work at MIT on that. So we're following that very intently. So I think for us, it boils down to quality of simulation. Can you simulate it in an auto-differentiable fashion? And then finally, just compute power so that we can run these very powerful optimization algorithms, including hardware, including domain randomization in reasonable amount of time. Then there's also a question, kind of a follow-up on the previous question on how do we represent tactile data so that it transfers well to the real world? Is it raw data or something else? And that's a great question, because what we're doing right now, we're not simulating raw data. Our sensors don't lend themselves to simulation because they have this very intricate way of light interacting inside the finger that gives us the raw data. So we are assuming a supervised tactile model that gives us location and normal force. So we are simulating a tactile sensor that just outputs location and normal force. We're not simulating raw data. Interestingly, at the ICRA VITAC workshop just a couple of weeks ago, we saw some really interesting work on simulating camera-based sensors. Right? We have that's the GelSight, the OmniTact, the Digit, from MIT, from Berkeley, from Facebook. Remarkable tactile sensors based on CMOS or CCD sensors. Our sensor is not like them in the sense that our pixels are distributed, if you wish. And we have the advantage that we can more easily build complex shapes and make them sensorized. Of course, a CCD or a CMOS sensor is going to have much richer data than we get. And the fact that they're making great progress in simulating those image-based sensors, to me, could potentially be a game changer. That people will be able to simulate the raw data coming out of those tactile sensors and thus train model-free RL directly on raw data from the tactile sensor. And that could be a game changer. It's something that I'm really excited to follow over the next couple of years.
Great, thank you. I think we can conclude the discussion session now. Thanks again for both speakers for giving the great talks and staying here for the answers. We now will have a short break. Of 35 minutes, and after that, the poster session will start.
Thank you.
Thank you.
Thank you, Matai and Parag.